How are you?
Good. How are you doing?
Not bad. Just enjoying. I like at this time of day. There's a lot of sun.
Yeah, it's sunny and nice. I give few more trials. And I don't know, yesterday not yesterday, a few days ago, when you tried to do it on the Google Colab, were you able to run it, to install it and run it?
Yeah. Oh, I never picked up on that. Like after my internet died.
Oh, okay.
You know.
Because I noticed that Kaggle and Google Colab is just going, and nothing is coming out.
Okay.
But the binder is working okay. Basically, people can run it through the binder. They can do experiments and see.
Yes, I will. Yeah, I'll look into the Kaggle and.
Matt, which notes should we be following?
Well, we're going to do a couple different things today, but yeah, on the site, there's a link, a little more on quantum reference frames. We're going to talk about that for a bit. And then also on that same page, there's links to these libraries that I wanted to just show off a little bit.
What's the title of your notes at, Red Hat?
Yeah, I just sent the link to.
Oh, okay.
Yeah, and I'll send these other links in there too.
Yeah, actually, if you could send them as you start them, that would be great, because we old people have trouble, following. We have to keep going back to
for sure.
Review what you said.
How's everyone doing?
So you're going to start with cubism?
We could take a little vote. Well, actually,
okay.
There's something that you'll like.
Sex?
Sex?
I'm here to meet women.
Wow.
I think you got to the wrong place.
Maybe.
I agree.
Maybe. I don't know.
I happened upon this on Twitter.
What happened?
Someone. Oh, can you see my screen?
Yes.
Okay. Cool. Sorry. Yeah, I happened upon this on Twitter. Little Python code for calculating Bohmian trajectories.
Oh, okay.
You can do it yourself.
Well, I know Bohm. I don't know Python, unfortunately. My neighbor who's studying computer science keeps telling me I should learn Python.
I like Python.
Yeah, well, that's what they're using these days, sure.
Yeah, it's an interesting kind of phenomenon, because I've used a lot of different languages over the years, but there's something I feel
what would you say is the main difference between Python and, let's say, C?
Well, there's many differences. I would say in general with Python, there's a kind of Goldilocks principle. It's just sort of just right for a lot of stuff. With regard to differences from C, Python's not compiled. So, that in general, it can be slower, although people have ways of, bringing in C libraries and more optimized stuff. One of the great things about Python is it's just the ecosystem of libraries is just extravagant. There's just everything. And the syntax is very flexible. It's a good mix of, object-oriented stuff. You can even kind of hack it to do functional programming, kind of redefine stuff. And the syntax is pretty, you know what I mean? When you first hear about it, you're like, oh, the white space matters, which was problematic for some people at the beginning. But, you can kind of screw with it a little bit. And I find it easy on the eye.
Yeah, in years of programming, I've only had one problem.
What's that, Marty?
Oh, in years of programming on Python, I've only had one or two maybe examples of having a problem with the white space. It's only at the end of a block that you have to worry.
See, yeah. Moshe and I are still using machine language. I don't know if that's
I used that for about 8 years.
Did you really?
Yeah. And C++ for another 8 years.
How does Python compare to C++?
Well, like I say,
Oh,
it's got objects. So
So you can define your own objects.
yeah, for sure.
yeah. It's
Okay.
much smaller than C++. It's much easier to learn. And I don't like C++ at all.
Yeah, and like just like the fact, I forget if in C++ there's like list comprehensions. I mean,
There are?
are there? I mean, it was
No.
like I don't think there are.
List comprehensions are the best thing. It's like mathematics.
Yeah, it's like the only thing. I mean, it's like
And
the greatest thing. Yeah.
in fact, I like Perl, and I program in Perl, and Perl 5 didn't have list comprehensions, but Perl 6 does.
Oh, interesting.
So they copied it from Python.
It's been many years since I used Perl. I remember being like it has a kind of brutal beauty to it.
Yes.
A lot of symbols.
It looks like modem noise.
Yeah, people have been buzzing about this language, Julia, which at some point I should learn.
Yeah.
Which has, so far as I know, kind of like not just list comprehensions, but like a lot of vector and matrix and linear algebra stuff kind of like baked into the language, making it really nice for.
What about R? Have you tried R?
I haven't.
No, it's very vector oriented.
Yeah, I think Julia was described as like a kind of mashup of Python and R. Maybe it may or may not be true, but
yeah, that helps.
yeah. Have you guys ever used any like functional languages? I mean, one of my friends swears by Haskell, which I've tried.
Yeah. I wouldn't swear by it. No, it's not. It's
He's
also
a mathematician, so
it's
What is that?
incomprehensible.
Haskell?
Haskell.
Eddie Haskell was on Leave It to Beaver. He was Wally's friend.
Oh no,
Do you remember
it
that,
must not have
Marty?
been the same Haskell.
Eddie Haskell. He was like
No.
he was a terrible friend.
I didn't watch
of Beaver's
family
brother.
comedy.
You didn't watch Family
No.
Comedy?
Well,
How about The Honeymooners?
Well, that's
still on.
that I watched.
That's the best
I
show that
think,
was
yeah.
ever made. You know that all of the episodes were recorded in a single season.
Wow.
huh. How many?
They were like one after another. And Jackie Gleason apparently had a photographic memory. He read the script once and he was ready. While everybody else was still, rehearsing.
Yeah.
I think Haskell, in fact, is named after Haskell Curry.
Right. Right. Haskell curry. Yeah, curried.
Of the
Is
curry.
that an Indian dish? I think I had that at the Indian restaurant.
No, not
near,
that curry.
But yeah, so I recommend this little tutorial. The Python code isn't very complicated, and they just do like a little kind of numerical simulation of a wave function going through a double slit, and they calculate the Bohmian trajectory. You can see the little particle there just jittering around. Oh, look at them go!
Wow.
Boom.
So is their conclusion that a particle goes through both slits at the same time, or just one slit at a time?
What is that little black dot? Yeah, he just went through one.
Right, exactly.
There he goes.
That's the whole point.
I mean, it's interesting, like looking at its speed. It's like it's not just that it kind of takes a funny trajectory, but it kind of like, moves around in a funny way.
Well, if it's massless, then it goes at the speed of light. If it has mass, it goes less than the speed of light.
Well, I just mean like it's not like it doesn't move like smoothly, I suppose. Kind of jitters.
Well,
but yeah.
Well, that's quantum field. Quantum field theory. A particle is not a point particle. It's
So I've heard.
a wave disturbance.
Bomb is not quantum field theory.
Bohm.
No, Bohm is not quantum field theory, but
Well-
Bohm is only an approximation.
Not to get too much into the Bohm thing, but like, have you guys read his book, like The Implicate Order? Like, it's kind of a crazy book. You know, I didn't realize, like, it's just full of these really pretty interesting essays. And I was surprised by, like, he's got really long one on like language and his like attempt to kind of like, in a very old school way, like invent all this new kind of like terminology and grammar to help sort of conceptualize an undivided world, you know.
But do you know his political background? That's a key to understanding a lot of his life.
Yeah, a little bit.
He was victimized by during the McCarthy era, and he went into self-exile. He was fired from Princeton University, and
No,
he
for
left
real.
the United States.
Michael, you keep telling us this at every single session.
But that's important, Moshe. That's why they don't teach it. They still don't teach
Yeah,
Bohemian.
okay, Michael, let me
Maybe.
tell you something that is going to really shock you.
But they don't teach it. They don't teach it as an alternative
Michael,
theory.
listen very carefully because it is going to shock you. I hope you are seated right now. We folks here at this session, we are not all of us a bunch of imbeciles. We hear it once, we get it. We hear it twice, okay, we got it. We don't have to hear it again every single session. We got it.
Okay, so why do I got your message? So why do we keep reading about Hugh Everett's many worlds theory? They put that in textbooks. Tell me that's not crazy.
But it's certainly true what you say, that the McCarthy era really sucked. I mean, I have a friend who's the child of someone who was a victim of that. You know, who's in show business, and you know, he was blacklisted and the whole thing.
Did anybody see the movie Trumbo? Dalton Trumbo was a screenwriter who was banned in Hollywood. He was the best screenwriter of his age. So you know what he did? He organized a bunch of screenwriters who were banned because they were accused by McCarthyism. And they wrote the screenplays, but they had to get fronts to other people, other screenwriters who were not as good. And the other guys got the Academy Awards.
Wow.
They didn't, until ultimately Trumbo eventually got his Academy Award. Trumbo, yeah, Dalton Trumbo.
About
Trumbo
that.
was the name of it. They made a movie recently, or I don't know, a few years ago. But this is what went on. I mean, it was a horror show, really, and it could happen again.
For sure.
That's the point. Yeah, and Woody Allen made a movie. Yeah, not Trumbo, but Woody Allen, The Front. He made a movie called The Front.
Yeah,
where
yeah.
I think Zero Mostel played somebody who was victimized by the McCarthy era. But that's what went on. We don't know that.
Zero was.
We weren't born yet.
Self-victimized by it.
Was that? Yeah. I mean, a whole generation of people in all different professions were victimized by it. And they never recovered. A lot of people committed suicide. They never recovered from it.
Yeah, and it wasn't that long ago. I mean,
it was 70 years ago, 60 years
50s,
ago, 70
yeah.
years ago, in the early 1950s. And
Yeah.
Richard Nixon was part of it. Richard Nixon started it when he was a member of Congress on the House Un-American Activities Committee. And that's how he actually made his name.
I was going to guess it must have been the Republicans.
Well, yeah, and McCarthy was a Republican. And by the way, you know who one of McCarthy's best friends was? Joseph P. Kennedy. And Bobby Kennedy was a counsel. He was a lawyer on the McCarthy committee. Of course, by the 60s, you know, they had collective forgetfulness about what they had done. Anyway, end of speech.
Anyway, yeah, moving right along.
Political detour.
Moving right along.
So yeah, today I just wanted to show off like a couple things. So, the past couple months, I've been part of this mentorship program as a mentee. My mentor Vesseline actually is here with us today. And I recommend checking out the Quantum Open Source Foundation. If you guys want to get involved in open source quantum software, they're having another mentorship program, cohort number 3. Applications are open now. And it's really fun. I recommend it. It's a good community of people. And so, as part of that, I put together this library spheres that, kind of packages up like a lot of the stuff that we've, talked about in these meetings. Basically, it's easy to install, just do pip install spheres. And I learned how to use Sphinx, which, is a way of making these professional looking documentation sites. And so, I recommend, poking around in here. Basically it provides a set of tools for working with the Majorana representation. So, dealing with these different representations of points on spheres, polynomials, quantum states, etc. And then also working with the permutation symmetric multi-qubit representation and the oscillator representation. And so, internally, you can kind of like go back and forth between these like different data structures, and indeed like generate circuits like we've seen, Qiskit circuits for, generating the qubit stuff, and strawberry field circuits. So, everything's just very heavily documented. You can go in here, spin to poly. Where is it? Like here's this is one of the workhorse functions of the whole thing. Takes a quantum state as input and returns the Majorana polynomial. And so, you can remind yourself of all the math here, and obviously check out the source code if you want. To the left here, I've got tutorials, which are like basically adaptations from the notebooks from the Brooklyn Quantum. So, this is like a little introduction to the whole formalism. And here's one about preparing the symmetric multi-qubit states, doing the photonic, oscillator states. This one's the whole thing about those like structured Gaussian beams of light that we were getting into at one point. These great pictures. This little bit about Majorana representation for mixed states and operators. And then finally, I mentioned in passing when we were talking about the symmetric multi-qubit states, this idea that you could use this for kind of like error correction. The idea being that you would run, you have like a certain quantum circuit, maybe it's like 3 qubits and like a bunch of gates. And you actually run, say, like a bunch of copies of that in parallel, and periodically like project all the sort of experiments into the permutation symmetric subspace. And the idea is like, this is the subspace that like, it's not going to affect what's going on. And it's the smallest subspace that's error free, because in theory, if all the circuits are working correctly, they should already be the same. They should already be basically identical. And so if there's some asymmetry, maybe you can project it out without, disturbing the computation. And so you can basically generate circuits to do that and kind of like, evaluate its performance. With current hardware, it doesn't work that well, which was a conclusion that kind of came to here. But yeah, I don't want to we have a couple new people here today. I don't want to bore you guys with stuff that you've already heard. But just like as a quick example, you go into Python, you can from spheres import all, and imports takes a second. And you can do stuff like, okay, let's generate a random complex number. There it is. Well, maybe we're interested in that in terms of like XYZ coordinates via the stereographic projection. So, this uses that map from the plane, the complex plane, to the sphere. Boom, there you go, point on the unit circle. Or maybe you're interested in, that same point in spherical coordinates, theta and phi. Or maybe you're interested in that same point in terms of like a spinner. Like this is a qubit whose expected rotation axis is given by that XYZ point. And, you can kind of like go back and forth, right? So if you have like C to XYZ, and then we can go back XYZ to C. So, you can basically easily work with different, coordinate systems on the sphere. If you have like a spin state, like let's say, a spin 3/2 state, it's like 4-dimensional. There it is. And, we can use this function spin XYZ to get the stars that we all know and love. There they are, 3 stars. And if you want to visualize it, you can just be like Majorana sphere, spin, and there they are. Look at that. This uses VPython for the graphics, which can work in a notebook and also stand alone, but doesn't always work, in which case you can also be like visspin, which will generate a little matplotlib graphic for you to play around with. How nice is that? You can do kind of cool stuff. Let me make another sphere here. Sphere. Sorry. No, sorry. Okay. There's that. So like we could go in and like evolve it under some evolution. We could like rotate it. No, sorry. So in QTIP, when you want one of the spin generators of rotation, you use this JMat function. So it takes the J value and the direction you want to rotate it around. And you can watch it go. There we go, rotating around the Y axis. And for example, we could also look at the phase. So, there's the complex phase of the qubit. And, we can look how that evolves, as we do a rotation. And, one of the nice things about this is it's all like live. So you can be like, take the phase away. You can be like, show wave function. So, there's this connection between the Majorana representation and spin coherent states. So if you recall, the spin coherent states have all the stars at one location on the sphere. And so there's a whole sphere's worth of them. And they form a frame for spin states of a given J value. And so you can think about the Majorana stars as basically being like zeros of the spin coherent wave function. And so basically what you see here are the arrows which correspond to the different amplitudes for this spin state on the spin coherent state with all the stars at that location. And like, so this is, so when you think about the spin coherent wave function, the idea actually is that the stars, the 0 points are like directly opposite the little points there. So that's true for the spin coherent ones, but you could be like, what is it? Wave function type Majorana. You can actually visualize like the Majorana polynomial, like evaluated at each point on the sphere. And their zeros are literally where these stars are. So the coherent state wave function and the Majorana function are actually antipodal to each other. Indeed, on that point, if we have our spin, we can, convert that spin into a Majorana polynomial where this is like the coefficients of the polynomial. But for example, we could also, right. We could also like have it return like a function that, is the Majorana polynomial. So you can like throw in, some value and evaluate what the Majorana polynomial is at that point. And one of the interesting things, like for example, I go into it here. You can actually represent the inner product in terms of an integral on the sphere of these Majorana polynomials. So we have a spin and like another spin. We can, calculate like the overlap between them, or like, spin dag times spin. There we go. That's the inner product between these two spin states. But we can also express that as an integral. So, okay. Spin, okay, what did I call them? Spin and spin 1. So if you pass this little parameter for integration, it just, oh, shit, what did I call it? Oh, spin 2. Spin and spin 2. Kind of inconsistent there. In order for this to work, you have to normalize them a little bit. So that's what this for integration thing does. And, if you're like, what is that? Where does that come from? I refer you to the excellent documentation. So for example, go back to that function here. We normalize by this little factor and also throw in this extra little factor too. And then, for example, we can use these functions, integrate them against each other using the integration measure on the sphere. And in theory, we should get the inner product back. Ooh, there it is. There you go. Well, I guess it's spin.dag times spin 2. There we go. So there's all sorts of stuff you can play around with. Like in terms of the symmetrization, right? So you can be like, okay, we got a spin state. But what would it be as a permutation symmetric qubit state? So we do sim to spin. So this takes us from our spin 3 half state that's 4-dimensional to this 8-dimensional state, which is like a tensor product of 3 qubits that are permutation symmetric. And you can even go in reverse, sim to spin. And it takes you right back where you started. So like a lot of this code is like conversions, right? Cartesian coordinates to complex coordinates to spherical coordinates, polynomial to its roots to a function to whatever, spin state to symmetrized state, even spin to oscillator state. There you go. Now we've represented the spin as tensor product of 2 harmonic oscillators with truncation, with the dimensions truncated at 4. And I think it goes in reverse too. Yeah, look at that. So, there you go. So yeah, maybe to go into this a little bit more systematically, here, spheres.coordinates, you have all your sort of coordinate transformations, complex numbers, spherical coordinates, Cartesian coordinates, whatever. In spin.stars.pure, we have all of our functions for dealing with the Majorana polynomial. So by the way, instead of doing spin to x, y, z to get the points in Cartesian, you could be like spin to c, and there's the points in, as complex numbers or extended complex numbers, because they might be infinity, and so on. Spheres.stars.mixed, you have all this stuff. We talked about this a little bit, for generalizing the Majorana representation for mixed states. So for example, we could have like a random density matrix, and then we could use operator sphere to visualize it, maybe. Oh, there it is. Oh, wait. We gotta destroy. Okay, there we go. Yeah, like for example, boom. Or if you recall, you know, the idea is that operators can basically be viewed as a bunch of concentric spheres. And we can evolve it. Why not? What was it? Spin 1 on the x-axis. Oh, sorry. Where is it? Oh. Need to make a new one. I forgot to save its the variable. That's annoying. No way around that. There's a way in Python of like being like, what are the variables in just the current scope, but I forget what it is at the moment. Operator sphere. Okay, now we're back. Let's do a X rotation. La 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 la. With this one, it's cool because the colors have to do with the relative phase between the spin states that correspond to the concentric spheres. Whereas in the Majorana sphere object, we represent the phase with like a little arrow. So there's that. You know, we had our beam stuff. Love the beam. So, you know, recall from our adventures with structured Gaussian beams, you could take a spin state. Here's a spin state and convert it into a structured Gaussian beam. So this spin to beam is, here's like the function, which you can evaluate at different points and get the, if you recall, like the amplitude and phase of the electromagnetic field, you know, of this sort of classical light beam. And then you can visualize it. Viz beam. Boom, there it is. It's like all this stuff, you know, basically that's like in the notebooks or whatever, you know, you would have had to copy and paste the code or like whatever. It's all just here waiting for you to use it, basically, if you're interested. Oh yeah, Viz spin beam. That should show the there's our spin and there's the structure Gaussian beam. Recall that's the cross section of the laser, basically. So got that going on. Spin circuits. Yeah, let's check that out. So we have a spin, and you know, we can convert it into a symmetrized multi-qubit state using spin sim, as we saw. So this is like a spin 1 state. It's got 2 stars, and so we get a 2 qubit state, permutation symmetric. But we could also just be like, hey, Qiskit, give me a Qiskit circuit that actually prepares that on one of IBM's quantum computers. So, you know, it actually returns a dictionary with some useful information. So for example, here's like the circuit, which I believe you can just draw. There it is. Aha, look at that. You know, recall the structure of it. We're basically, you got 2 qubits. We rotate the 1 qubit so that it's, you know, it starts off pointed in the Z+ direction. We rotate it to the direction of one of the stars. Take the other qubit, rotate it in the direction of the other star, and then use the control qubit to sort of symmetrize them. But it's a probabilistic algorithm. So we have to measure the control qubit and post select on it being 0 or up, in which case it will have worked. So, you know, you can, it additionally, like in this dictionary, you know, you can be like, oh, what's the quantum register for the spin qubits, the control qubits? You'd be like, which one are we supposed to post select on? You know, yeah, control bits. And what's like the post selection supposed to be? Oh yeah, they're all supposed to be 0. And so, for example, there's like a function here that like, if you, once you get your results, you know, this will like perform the post selection. Qiskit doesn't really have like post selection stuff kind of like built into it. So whatever. You know, you can test that it works. So for example, once we have this, we can just be like spin tomography Qiskit circ info. And what this will do is it will, well, it's running it on the local simulator, but you know, you could, there's a parameter you can pass in here to run it on, you know, the quantum cloud. But you know, this basically like runs the circuit a bunch of times. In fact, many, many times, because it also does tomography or state reconstruction on the circuit. So, you know, this basically like prepares the symmetric multi-qubit state and then tries to like recover what that state is to make sure it works. And so this is the density matrix that it recovered. And we can see that it did pretty well because this is the density matrix that we started out with. So, you know, we, again, just ran this locally, but, you know, you just type it, you know, you just, there's a parameter here, backend name. So you would just, you know, log in, make sure you're logged in to IBM and just put in the name of the quantum computer you want right there. And, you know, we can do the same thing with the oscillator stuff, right? So spin to OSC takes us from spin state to, you know, the oscillator representation of 2 harmonic oscillators, where, you know, it's like the second quantization of a qubit. One oscillator counts the number of up quanta, the other oscillator counts the number of down quanta, and you can define XYZ operators as, you know, kind of built out of the creation and annihilation operators of the, you know, 2 modes basically. And so that's cool, you know, whatever, we have this little vector right here. But so spin OSC strawberry fields straight up returns a strawberry fields program that when you run it, you know, will prepare this state on, well, the local simulator, but ultimately their photonic quantum computer. And, you know, I refer you here just to, you know, for your memory, like you end up with something that looks like this. Basically a bunch of beam splitters and post-selection. You kind of have a bunch of pairs of oscillators, load in a quantum into each one, kind of like rotate it so they're pointing the directions of the stars, and then post-select in order to kind of force all of the stars to be in 2 of the oscillator modes. And, you know, on that note, you know, for dealing with these kinds of oscillator type stuff, there's a whole set of kind of useful functions for dealing with symplectic transformations. So, you know, if you recall, we, you know, did a whole thing about sort of the relationship between symplectic transformations and second quantization and all this other stuff. And so, you know, you can take, you know, these are basically functions for converting from Gaussian, you know, Hamiltonians, which are, you know, linear, quadratic in creation and annihilation operators, converting them into complex symplectic matrices, real symplectic matrices. And, you know, these can act on, for example, the first and second moments of Gaussian oscillator states. And so this is useful for dealing with all that strawberry field stuff as well. And yeah, visualization, as I say, we got some matplotlib stuff, to use in a pinch. Majorana sphere is kind of the workhorse for VPython, visualize the sphere. Operator sphere allows you to visualize density matrices and operators. Schwinger spheres is for visualizing these oscillator states. So if we Schwinger spheres, Julian Schwinger loved this stuff. So, destroy O. Let's see, our little operator guy is still in there. So here, the idea was that you can take the double oscillator states and view them as a tower of spin states. And so here we have a little spin 0 sector, a spin half sector, spin 1 sector, spin 3 half sector, spin 2 sector, and so forth. And indeed, it's like, here was our original spin. And let's just look at that Majorana sphere spin, and we can let's put it in a different position so we don't get some overlap here. Let's put it there. Boom. So there was the spin. And you see, when you visualize, the oscillators right there sitting in the spin 1 sector is the spin that we wanted. So you're that it works. So yeah.
Can I ask a question?
Mm-hmm.
Schwinger, even before Feynman, I think, really popularized, we wouldn't call it a path integral, but the action integral. Does this relate at all to that? I mean, do harmonic oscillators relate to his?
Not directly, so far as I know. I mean, the story I heard was that Schwinger, as a young man, maybe 18 or 19, I think in the 40s, discovered Majorana's work from a decade previous, right? So in 1932, Majorana comes up with the constellation representation. And Schwinger read about it and was like, what the fuck? I don't understand why this works. And so
I don't think he put it quite that way. Not in front of his mother, anyway.
And so, I don't know if the oscillator representation was known. In theory, those three ways of thinking about it, a spin as a sort of polynomial where you have the unordered roots, and then you have the spin as permutation symmetric product of qubits, which by permutation symmetry are unordered, just like the roots in a polynomial. And each one of those is one of the fundamental representations of SU2, right? Spin half. And so you can build up, in this case, the higher representations, for higher spin J values, with these combinations of the spin half representation, which is then, basically really the same thing that's going on in the oscillator case, because basically the oscillators keep track of a certain number of unordered or bosonic quanta, each one of which is basically a qubit. And so in some sense, it's all really the same story told in different ways. I don't know if Majorana was thinking in terms of, I don't even know if he thought in terms of the permutation symmetric stuff or the oscillator stuff, but certainly Schwinger, brought up the oscillator stuff. And I know that and I don't know, I mean, at this time, I don't know that much. I mean, I suppose it's sort of the history of quantum field theory in this time period is is sort of, it's not something I've fully have internalized, because obviously it was a period of great, disagreement and sort of ferment, and people not being sure what to make of it. And, what, this idea of sort of second quantization and all this other stuff. And physicists at the time are still kind of internalizing group theory, which is really at the heart of why this works and all this other stuff. So you know.
There's actually an excellent book by a physicist about the early history of quantum field theory. You know, with Schwinger and Feynman and
Mhm.
is it Tominaga, the Japanese the physicist,
Right.
by Sylvan Schweber.
Yeah, write it down.
I try to get that book in the library, but I haven't been able to. And I'm a cheapskate, so I'm too cheap to buy it. But it's I understand it's an excellent history. Schweber, the I can't remember the name, but it's the early history of QFT.
Very cool. Very cool.
And then they say, that physics really, modern physics is really about the study of and the refinement of harmonic oscillators. That's what it's all about.
Well, that's what's going on. Although, you know, what can you say? But that's, I mean, you could say this same thing about, you know, a lot of fields of mathematics, you know what I mean? Like, why do we, you know, there's an intimate relationship between harmonic oscillators and like Gaussians, and Gaussians are really easy to work with. So, you know, it all makes sense from a practical perspective. So yeah, like any questions about any of the spheres business? Got, you know, a bunch of kind of useful kind of utility functions. You know, I use this library all the time. Like when I'm just screwing around, exploring new quantum stuff, whatever it is, I'm always importing spheres. You know, whenever there's like something that QTIP or, you know, NumPy doesn't have, I'll like throw in the function here, you know, just look at the stars if I'm like worried about like, what is this quantum state? So, you know, it's nice to have around. You know, if you do happen to check it out and you find a bug or something, you know, let me know. I'll get on it. Yeah, I recommend you all check out the Quantum Open Source Foundation. There's a, you know, that reminds me, like if you go on the GitHub, there's a little, you know, if there wasn't enough documentation, there's a little PowerPoint slide here. Gives you the short version. Look at all that summed up. Just a couple of pictures. This one was popular. So yeah, so there you go. In other news, working on a new library. It's on the theme of software. So, you know, last meeting, we talked about cubism, which is my, you know, which is cool. I like cubism. And so I kind of like packaged up the tutorial, you know, which I basically talked about last time. You can now find it here on this page. I mean, it's in slightly updated form, but you know, similarly to spheres, where like I took the different tutorials and kind of packaged up the code into a library. Here, you know, you can just be like pip install cubism and just get all these useful tools for dealing with cubism, you know, for free. And you know, specifically, when we say cubism, I mean, there's, as we talked about before, this whole kind of interesting philosophical component to it. But, you know, practical payoff is maybe you're interested in POVMs, or these positive operator valued measures. And, you know, we showed last time how you can represent all of quantum mechanics in terms of probability distributions on POVM elements. So you can kind of take your quantum state, instead of like working with a density matrix or whatever, you can find its probabilities for a given POVM, like a informationally complete POVM that you like. You get a probability distribution. And then you can kind of construct conditional probability matrices for any other measurement you might do. And there's just an easy way of calculating like all the probabilities for any, quantum measurements, including, time evolution, all this other stuff, directly in terms of the probabilities. No amplitudes, no complex numbers. What? How is it possible? In the little tutorial from last time, we, focused sort of specifically on the case of these magical seq problems or symmetric informationally complete problems. But here, if there's actually tools for working with more general problems, which you can generate using the Weil-Heisenberg group. If you recall, this sort of the upshot was basically like, just to remind you, suppose we have a density matrix. We generate some informationally complete problem. If we're in D dimensions, there's gonna be D squared elements. We can get the probabilities. These 4 probabilities actually determine the quantum state. One measurement. We can, here, we sort of, where was it? We sort of described like, right, these sort of quantum probabilities using formulas that look like this, if you recall. And there's like a sort of a more general way of writing these equations as like matrix equations that allow this to be applicable, not just for the special seq problems, but for any informationally complete problem. So you form this matrix called phi. And the point is that if you then have like a measurement that you're gonna do, represented by a Hermitian matrix, you find the projectors, you can get the classical probabilities. In other words, you have a quantum state, you do this problem measurement, there's an outcome, but you don't know which. So you have these sort of probabilities. And then you do this von Neumann measurement. The probabilities are given by the probabilities for the different problem outcomes multiplied by the conditional probability matrix for one of the von Neumann outcomes given a problem outcome. But then you're worried like, but what about the probabilities if I didn't do that problem in the middle? What if I just went right to the von Neumann measurement? And you can see that all you do is stick this matrix phi in the middle between the probability vector and the conditional probability matrix. And so like all of the quantumness is kind of hidden here in this matrix phi, which, I go into a little bit like how we calculate it here. Basically, you sort of take, it's sort of like you calculate basically like the gram matrix of inner products between the different problem outcomes and then take its inverse. And in the case of seq problems, it's been proved that this matrix phi will be as close to the identity as possible. So you see here, like these classical probabilities, quote unquote, it's like as if phi is just the identity. And so specifically for seq problems, phi is as close to the identity as possible, sort of minimally quantum. It's kind of an interesting result. And so, you can sort of represent time evolution and even, partial traces. Like one of the things I added to this that we didn't talk about last time was there's a sort of general idea of a Krauss operator. And so you can sort of represent the partial trace as a Krauss operation. In other words, you have a bunch of Krauss maps that are basically transformations of density matrices. You have like a list of Krauss operators and you kind of wedge your density matrix in between them and do that for each Krauss matrix and then sum over all of them. And you can, write the partial trace in this term, in these terms, and then you can actually represent that map as a matrix that acts on your problem probability vector. So, you can really represent pretty much like all of quantum mechanics with these probability vectors. So anyway, I don't know if maybe I'm going a little bit too quickly, but we did talk about this last time. Again, if there's any questions, please ask them. basically, the different sections here, tools for dealing with the Weil-Heisenberg group, the seq problems, as we mentioned last time, that are known. Almost all of them are covariant under this group, and we kind of use this group to generate them. There's some tools for dealing with the seq problems, generating them, getting their Graham matrix. There's the exceptional seq problem in dimension 8, the Hogar problem. You can play around with that if you like, it's in there. Can't forget that one. General stuff for dealing with problems, calculate the Graham matrix, calculate this magical quantum coherence matrix, phi, get a measure of the quantumness, convert from a density matrix to the probabilities, from the probabilities to the density matrix, get a matrix of conditional probabilities, and you can represent, time evolution, you can tensor the problems together. You can implement the problems. Remember, really what you're doing is what this cashes out into is like you have an auxiliary system, which has as many basis states as problem elements on the original system. And then you apply a unitary operator that entangles your auxiliary system with the system that you care about, such that the probabilities on the auxiliary system's basis states are the same as the probabilities that you calculate like on the problem elements. And so, you can sort of get a concrete representation of it here. And this is interesting. Here, maybe I'll just dwell on a moment on this. I feel like Moshe, you would like this. It just reminds me of something you brought up over the summer, namely like sort of this question of like, is there a way of just telling like whether two quantum states are the same or not? Like in a way that's basis independent. And we ultimately decided like, no. But this is kind of like an interesting thing that you can do. So, so this is a sort of so-called discriminator problem. So this is a problem that has the special property that it can like just distinguish between two completely arbitrary states. This is kind of surprising that you can do this. So you just have like a state A and a state B. They don't have to be orthogonal, whatever, doesn't matter. Any two states. You then form three problem elements. This one, basically, you see identity minus the projector onto B. In other words, this one tests that you're not in the A state, or sorry, excuse me. This one tests that you're not in the B state. This one tests that you're not in the A state. And this one sort of is like neither. So basically, if you look at the probabilities for this problem, say if you're in the A state, here they are. This is the probability for this first outcome. This is the probability for the second outcome. This is the probability for the third sort of inconclusive outcome. And you can see that the probability is zero. If you're in the A state, the probability of it being B is 0. This one is if you're in the B state, the probability of it being in the A state is 0. So in other words, this is a measurement that you can do that can like reliably distinguish between two arbitrary states. What's the catch? Sometimes your answer is just like inconclusive. Kind of cool. Kind of cool. I like that. So cool things you can do with positive operator valued measures. Here's stuff, as I mentioned, with the Krauss operators. You can apply Krauss transformation to the density matrix, etc. Here, like this is what I was saying about the partial trace. So for example, I can generate the partial trait, like a set of Krauss operators that implement the partial trace, and then represent it as a matrix that like acts like a conditional probability matrix, but like actually takes me from my probability distribution on problem outcomes for the tensor product to probabilities for the partial state. And it looks just the same. So, Here's the probabilities for the tensor product. We stick a phi matrix in the middle, and then we have this matrix which actually implements the partial trace. And you know, if you're exploring the stuff, a useful thing to do is to be able to generate, like, to sample from the space of problems. So this, you know, is adapted from this paper and blog post. You can generate, you know, Haar randomly distributed problems in different dimensions. You can just be like, what's my dimensions? How many elements do I want? Kind of a parameter that gives you the mixedness. If you recall, these problem elements, in the case of a seq, they're rank 1, so they're like projectors, and so correspond to states. But in the general case, they can be mixed states. And so if this number is greater than 1, they'll be mixed. And you can also generate problems in for real vector spaces. And actually, that's something I'm thinking about now. Reeks, real informationally complete problems. So, you know, the same trick works. Like, you don't need to do it in complex vector spaces. You can also explore sort of quantum mechanics in, you know, real vector spaces if you're interested, in which case the informationally complete problems, like in the case of complex vector spaces, they have like d squared elements, but they only have, you know, d squared plus d over 2 elements for real vector spaces. And so this is like some tools for dealing with that. Generate like random real, you know, quantum states, random real density matrices. Observables in real quantum mechanics aren't represented by Hermitian matrices, but by symmetric matrices, which are just like equal to their own transpose. And time evolution isn't represented by unitary matrices, but orthogonal matrices, which when you multiply them by their transpose gives you the identity. And so you can see all the same tricks for working with problems work in that case as well. So, so yeah, that's cubism. Again, you know, if you try it out, let me know if you find any bugs. I'm sort of continually working on it. And, you know, unlike with spheres, I use this useful library that, like, if any of you develop, you know, software libraries, I recommend this. It's called NBDev, and it allows you to kind of create like a Python library entirely with notebooks. So, like, for example, like I can just show you. So here's like my notebooks for cubism. Each of those pages is just this like Jupyter notebook. And like there's these directives. So like this means export this file as like Weil-Heisenberg.py. Like that's what's going to appear in the Python package. And then any cell that has a little hashtag export is like automatically exported to the file, to the library. And further, so, you know, basically it allows you to like write your code, you know, you have your, you know, your kind of like your documentation within the code, you have your explanations like in between the code, it automatically gets exported to the library. And then any assert statement is treated like a test. So you basically combine your code, your documentation, and your tests all in one. And then you basically, like I'll just show you how easy this is. You know, you've been working on your notebooks, and then you just sort of like build the library, and it like reads through all the notebooks and generates just like the Python code. So here's like a folder cubism. And so like say from the Krauss notebook, it generated, you know, this, which like is just like in a normal Python library. Furthermore, you can just be like, test the notebooks. So this like goes through all the notebooks and like finds all the assert statements and like runs them all and makes sure your tests are passing. And finally, this, well, it's gotta take a second. There's this command, build docs, which by the way, you should, you know, you sort of have to use Jekyll, which is a Ruby-based like web thing, which is the sort of favorite thing for developing sites on GitHub pages. So build docs, build the documentation, and you can you know, look at it locally. So it's serving it up, and we, oh, excuse me, I already have it running. How convenient. So here it is, running locally to kind of like test it out. And when I push all the stuff to GitHub, you can see here, it basically, there's a GitHub action that, you know, kind of like installs the library, like runs all the tests in the notebooks, updates the documentation, does it all behind the scenes, so that just like automatically, if I go to heyredhead.github.io/cubism, all the stuff is right there. And you know, you can also very easily just be like, make release, and that'll update the PyPy package. So, you know, like for example, like with spheres, it was like, you know, if you look, where is it? You know, it's fine, but like, okay, I have all my code here and it's got, you know, the documentation in it or whatever for each function. That's cool. But then, you know, the notebooks that were the, you know, tutorials are different. And then like in each of these files here, I have all the different tests to make sure everything's like working and everything. It's kind of satisfying to be able to, you know, they call it a literate programming paradigm. The code and the explanation of the code and the test that the code works, all the same place, integrated. So I have had a nice experience with this. So I recommend that. So that was topic 2. Topic 1 was spheres. Sorry, topic 1 was spheres. Topic 2 was cubism and library. And then the last thing was I just was going to show like some cool stuff about quantum reference frames. But you know, any thoughts or questions about cubism or any of this software stuff?
Yeah.
I would like to make a comment for folks in this group. I think that this is something that is very impressive. I think it could be very valuable for all kinds of people. I'm not one of them. And me, it is wasted, which is a shame because for lots of other people, it is very valuable. Now, beside this group, I'm also participating in the New York Quantum Theory group. I guess other people who are present at this session right now are probably participating in other groups as well. I would very strongly suggest that at other related groups that you participate in, bring it up. Let them know about this wonderful resource that is available here, so that other people may benefit from it as well. I'm afraid that at this point, there are lots of people who could benefit from it, who are simply not aware that this resource exists.
Right.
Yeah, thanks for saying that. You know, I find
Spread the word. Spread the word.
Yeah, you know, it's like the great thing about, you know, making software is this kind of frankly like it's easier to learn like a lot of this stuff when you have some software to play around with, right? It's like if you're just thrown in the deep end and they're like, okay, you got to solve this integral and you got to do this, and you got to do that. It's sort of like it's really easy to, you know, stray from the path basically. But you know, if someone's got like a software library, everything's checked, everything's tested. Even if you don't understand it yet, you can at least do it, you know, and play around.
Yeah. And yeah, one quote that I've heard was that the source code is the best documentation. Like it's reality.
Yeah, I agree. And, and that's why I like this literate programming paradigm, because, the, it's made me even approach my code itself in like a more pedagogical way. You know what I mean? I used to be very kind of like, a little bit sloppy with my variable names and stuff. But like when I'm like in this mode of like, people are going to see my code, and like I kind of want it to be as elegant as the explanation and the math that's around it. It kind of forces me to like be a little bit more, considerate about how I write the actual algorithm.
I wanted to ask you, do you have to use HTML or JavaScript?
For NBDev.
Yeah, or yeah, the other what
Yeah,
was the last thing you had?
Not at all. Like basically, it's all just taken care of. Like in other words, I just like write the stuff in the Jupyter notebooks, and so that consists of Python code, and then also, like these markdown cells, so they can contain markdown, and also like HTML. So there is like a little bit of HTML in there for sure. And then, no, it basically like translates these notebooks both into Python code for the library, but then also into, the HTML and everything for the website. So you don't even have to worry about that.
Okay, the reason I'm asking is because I would like to use D3, as a graphics system for doing Swarm, like graphics. I would like to do like the evolution in a swarm. And that's good because it can do that much computation, and it uses the client's machine, so it can do it quickly.
Nice, yeah.
In other words, when you're showing all this stuff, well, the Python is on someone else's server, I guess, or
right. Well, so yeah, so that's the thing, right? So the website that is generated is like basically static, right?
Yeah.
Now, oh shit. Now, like this site, by the way, how do I do this? So this is just also Python notebooks, but this was like, I made this back in the old days, I suppose. So I really just, yeah, where is it? I just have like a little script in here that builds site that just like converts all of the Jupyter notebooks into, HTML with a template, and then commits it to GitHub. And then, behind the scenes, like if you have GitHub pages set up, it just automatically becomes this website. But then of course, you can also use Binder. So I don't know if you guys ever click on this link, but this will open up a binder. In other words, there's a server somewhere that's spooling up, and it'll allow you to run the Jupyter notebooks basically on the cloud. So, so like, as you said, right, like that JavaScript stuff is great, because you're basically like running it on the client's, computer. And this Python stuff is harder, it's harder to use Python to do that stuff. It's easier to like work server side, unless you have some way of dealing with Jupyter notebooks. Now, there's like a lot of services like this one.
Yeah.
Vesseline is always suggesting using Kaggle. So you can sort of share the notebooks and stuff. But the way Binder works is you basically just give it a Git repository, which ideally has like a file in it, like an environment.yml file that tells it which libraries to install. So that's what it's doing right now. And then, and this is all free, by the way.
Oh.
And then you'll be able to just hop onto the notebooks once it's done loading. But
Yeah, that was something that we talked a little bit at the beginning of the session, that I was trying the Kaggle and the Google Colab, and we were, at least I wasn't able to get it run it, but through the binder you can run it.
yeah, I wonder
So
about
you can experiment that way. I mean, you can see different parts, how they work.
in the past. I found stuff like, Q-tip installs Python, which like is like a little heavy, because it has like a lot of like sort of C sped up libraries, and then like VPython, doesn't work with everything in the world. So yeah, your mileage may vary on a lot of this stuff. Oh, but while we're waiting for this, like, but Marty, I was going to mention, it's amazing to me how much stuff there is in JavaScript these days. I mean, like just like a year or two ago, I wanted to do like more quantum JavaScript visualization stuff. And it was like a pain in the ass. Like a lot of the stuff I was doing at that time was basically like, you'd have some kind of cool 3D visualization with Three.js, which by the way, if you don't know about, is great. Love this. Great, fucking amazing JavaScript graphics library. I suppose D3 is more focused on like data visualization, but this is like, you can make, video games in this thing. And the documentation is just to die for. Like the examples, like look at it, just click in examples. They got all the code for this. It's all free. Do anything with it. I love it. Look at that. Oh my God.
That's great.
So fast. I know, it's like unbelievable. Look at that. Whoa, we're just in this world now. So I would, but like, the thing is like, I wanted to run these quantum calculations behind the scenes. So like, I would have like a server side, like Python thing that would like, communicate with this JavaScript front end using sockets, and like everyone would have to like sync up and stuff. But these days, I mean, you can get like TensorFlow, JavaScript version. I mean, I'm not sure how long they've had that, but there's like another one like JavaScript Tensor library. There's another one as well. I forget what it's called. But yeah, but there's basically, for like a while there was like a moment where there wasn't that much good like math stuff basically available on JavaScript, but that has changed. So you can really do some cool stuff entirely in JavaScript.
Yeah, another reason why I was going to JavaScript is, well, it works in a notebook, but I wanted to ask you if you've ever used JavaScript, because I had trouble going from one cell to another in JavaScript, because JavaScript has some kind of, what is it, localization problems. Things have to be global. Either they're global or completely local. So you can't just do something in one cell and see it in another cell, which is horrible.
Huh. Wait, what were you using to write the JavaScript? You were in like a notebook type thing?
Yeah, and you could, you could just say this cell is JavaScript.
Right.
Or HTML.
What
and
is
then
that? There was I forget what it was called. There was like a there was like a especially I forget what it was. Yeah, there's several different like people who provide like notebook type stuff where you can have like different programming languages, including JavaScript in the cell.
Yeah. Actually, I'm using Perl.
Nice. That's cool. But yeah, I mean, I've honestly never used JavaScript in a notebook environment. Whenever I would work with it, it would be pretty much just, like in a just JS file. And but
That's because you didn't start working with the quantum music composer.
yeah, that's probably it. But yeah, there's something else.
Actually, it was music. Yeah.
TensorFlow, JavaScript.
Yeah.
Yeah, JavaScript's nice. It can be very, it's a little weird at times, but it's also kind of a flexible language.
Oh, yeah. Yeah. If you have a good background in C, you'll you'll do well in JavaScript, I think.
Yeah, for sure. That's true. Oh, here we are. Look at this. Binder opened up. And so you can, run all these notebooks yourself. Ooh, I should clean this out a little bit at some point. I don't know, like where's the one for today? Here it is. A modest one. But, it needs to be like, boom, run the cell. Doesn't do anything right now. I mean, there's no output to this cell. But hello. So if you do want to like share your Python code, especially if it's sort of like rich, the notebooks are definitely the way to go. But yeah, I've never used D3.
Yeah. Well, what I like about it is you can have interactive graphics in it.
Yeah, I from time to time I try to do it in Python and I always get very frustrated. It's like, what was I using the other day? There's oh yeah, Plotly. I kind of haven't had a mixed experience with Plotly, but in theory, it's very similar. But it sort of have like a relatively lightweight way of kind of creating like widgets that are written in Python that talk to a server and are able to you're able to interact with them live.
Uh-huh.
Yeah, I'll send a link to
Oh, check that out.
for you. Plotly. So yeah, well, I guess before we, call it a night, let me talk a little bit about quantum reference frames. At some point like over the summer, we talked about quantum reference frames a little bit. And then at Moshe's meeting a couple weeks ago, when I was talking about puzzles of supervenience in quantum mechanics, I brought up quantum reference frames. I never really showed like a really cool like visualization of it to just sort of like get the intuition. So I just happened to put that together. So I thought I would show it to you. But just so like a brief reminder of what it is. So, the reference frame is important. It's important often calculationally. It's important kind of philosophically. Here in little cell A, we have an example of, what's essentially a classical change of reference. So we have three particles, say, A, B, and C. And here, basically, we're imagining that C is just at the origin. Okay, so we're in this like reference frame where we decided C is at the origin. And in terms of that, A is this like little wave packet over here, and B is this little wave packet over here. Now you can imagine like, well, what would it be like if A was at the origin? Well, what would you do? You just pretty much just like move everything to the left. And so, now A is at the origin, so, C is to the left, B is to the right. Nothing too complicated there. But the idea is to sort of expand this notion to the case like where, explicitly, your reference frame is quantum mechanical, where you could be like, hey, I'm in a reference frame and I'm like looking at some other quantum system. And I'm like, well, like, what if I took that guy to be sitting at the origin? What would the physical state of the world be like from that perspective? And so people have been trying to formulate this theory using a principle known as coherent change of reference. So the idea of that is like, here we see in cell B, got C at the origin. We got A in a superposition of these two different wave packets. Then we got B over there. So this is from C's perspective. And now we're wondering like, what would happen if I took A's perspective? Well, then, A would be just like at the origin. So then the question is though, like, what would C and B look like, given that A was in a superposition of like being in two places? And the idea is of like a coherent change of reference is to basically consider all of the possibilities coherently. In other words, when you look at this case, we go from C to A. And so, C is, if A is to the right of C, then over here, C is to the left of A. Over here, we've done the same thing, but just twice. In other words, if here, C is just like in a separable state, is at the origin, and A is the superposition. If you were A here, then you'd see C in a superposition. Because if you look, suppose A was just in this part, then C would be over here, right? So that's just this guy, right? And if, A was here, then it would be like this longer distance to C. And so that's that. So this, preserves the relationship, between A and C, but in a coherent way, where you're like allowing, actually them to be in superposition. But then you go look over at B and you're like, okay, well, like if A was here, then B would be there, there'd be this distance between A and B. If this was A, then there'd be that distance between A and B. And so here just as well, B appears to be in a superposition of two different locations. But not only that, but C and B are going to be entangled, not just in superposition, but also entangled. Because like, if you think about it, it's like, well, if A had been just like at this part of the wave packet, right? Then you'd have this distance to C and this distance to B. In other words, that would be like this case and this case. It's like the closer wave packet here, and then the farther wave packet here. But if A was here, right, then, you'd be considering, this farther distance here, this one entangled with this one that's closer, because this is farther and this one's closer. So the idea is that in this framework, one is encouraged to look at things like entanglement and superposition as being observer dependent. In other words, I'm sitting here, I'm C, B is in a separable state, A happens to be in a superposition. What would it like to take A's perspective? Well, then C would be in a superposition, B would be in a superposition, and in fact, they'd be entangled. So that like, whether something's entangled or in a superposition would, be relative to, whose reference frame you're talking about. There's interesting questions here. Think about like the ability to like empirically confirm this kind of stuff. But actually, there's some interesting papers that I haven't fully internalized, where they'll be like, like in quantum field theory, it's sort of a question about how to define spin in a particular way, because you kind of want to, in order to define like the spin vector, you kind of want to like perform like a boost to a rest frame and then look at the spin in the rest frame. But what if this particle is in a superposition of, different momentum modes? how can you find the reference? How can you find the rest frame of it? If it's in a superposition of moving at different speeds? Well, you can use exactly this framework. You could coherently, do all the different boosts at once, basically. Like just there's no problem if you're allowed to do a coherent change of reference. Even if you're in a superposition of moving in different momentum modes, you can always find the rest frame to find the spin there. The cost is that other things are going to end up in some entangled superpositions that weren't from the other point of view. It's kind of practical value there. So, in this case, we are basically discussing, wave packets on a line. But we could also, think about the case of qubits. So like, for example, suppose A is the reference and the reference is like Z plus. And B and C are in a entangled superposition, up, plus, down, down. What happens when we switch to B's perspective? Well, by definition, B is going to be Z plus. Well, but if from A's perspective, B and C were in the entangled state, up, plus, down, down, then, if B is up from B's perspective, then C also must be up. They have to agree. So they're just in the up state. But what should A be? Well, from A's perspective, it was 50-50 whether B and C were each, up or down. So therefore, from B's perspective, B and C are both up, and A is in a superposition of being up and down, aka pointed to the right. So let's look at it. Let's take a look at an example of this. So actually, first, let's look in the case of particles on the ring. Ring QRF. Oh dear. Here's a programming thing. I love this website. Tabs to spaces. We were talking about, Python dealing with white space in a funny way. Sometimes your stuff gets corrupted. You go on this site and fix it for you. Okay. So what we have here are 3 particles on like a circle that's like been discretized, okay? So we basically have 8 locations on the circle that they can be in. There's red particle, blue particle, and green particle, okay? Now, this is the origin, okay? So from Red's perspective, Red's at the origin. He's just sitting here. And I've had it, the starting configuration to be that, green's in position 3 and blue is in position 5, okay? So, if you were red, you'd be like, okay, green's to the right and blue's to the left over there. Here, we see the same thing from, actually, let me make it a little bigger, from green's perspective. So from green's perspective, green's at the origin, okay? So if you're like sitting here, oh yeah, for green, red's to the left and blue's to the right. Green, red's to the left, blue's to the right. And similarly, if you were blue, you'd see green and red there. So far, this is just normal switching reference frames, like nothing quantum about this yet, okay? But for example, just, we can like look at it like, let's evolve this under the shift operator, basically. So this is evolving green guy around the circle from red's perspective. So there's green guy, he's zipping away from red, going around. But then interestingly, like if you were blue guy, right? Obviously red standing still, and they also see green moseying around. But the situation actually is a little bit different. Like if you were green, during these periods when green is in a superposition of being in two places at once. That's sort of a minor detail, but the main point is that mostly it's classical. So like green would see both red and blue kind of swinging around it. Okay. Anyway. Well, maybe I spoke too soon. Maybe, yeah, no, like I scratch what I just said. No, this is totally classical. Yeah, of course. Green is just sitting there. And so they see blue and red just moving around them. It just looks confusing because like the circles don't move kind of continuously along the circle, but kind of, kind of like creep from one discrete position to the other. Okay, I got confused for a second. Okay, doesn't matter. Let's move on to the quantum case. So here, what we've done is we've started out from red's perspective. Let's say red's at the origin. Green is in position 2, but blue is in a superposition of positions 4 and 6, okay? So here, red obviously is just at the origin, green's in a perfectly definite state, but blue is in the superposition. Now we can switch over to green's point of view. Nothing kind of funky happening there, right? It's just this kind of rotated, right? Green sees red in a perfectly definite position, and blue's in a superposition as well. But then the case is sort of more interesting when we're like, well, let's take blue's perspective. And so, blue is at the origin. And so the idea is like, think about this, like, suppose blue is here. Then green would be to the left like this, and then red would be opposite blue. Okay, so green to the left. So then you're looking over here, here's blue, green to the left, and red opposite to it on the sphere. But suppose this was blue. In that case, red would be to the right here, and green would be opposite. So then you look over here, here's red to the opposite, red to the right, and then green opposite to it. So in other words, both possibilities have been taken into account at the same time. And so if from red's perspective, blue is in a superposition of two places and green's just chilling there, then from blue's perspective, red and green are both in an entangled superposition. And we can do the same like evolution and kind of see what goes on there. Kind of cool looking. And if you want, you can like measure these things. So like let's measure blue from red's perspective. And blue collapses to one particular state and whatever. Okay, let's look at another example. So what would it be like if blue and green were maximally entangled and kind of like in a superposition over the whole ring? So, red from red's perspective is just chilling there. And from red's perspective, blue and green are in an even superposition over the entire ring. In other words, I've taken like for their state, the tensor product of like, all of these states where they're in the same location. 0, 0, plus 1, 1, plus 2, 2, plus 3, 3, etc. But then you wonder, okay, so what would it be like from green's perspective? Well, instead of red would be the one who's in a superposition over the whole ring, and blue and green would be in the same location. Because you see what's going on here is that like, no matter where blue and green are, they're in the same location. Like in other words, like this entangled state, it's like either they're both here or they're both here or they're both here or they're both here. So if you took blue and green's perspective, then blue and green would just be at the origin together. And it would be red who's smeared out over the ring. And similarly here, blue and green, red would be smeared out. So that's the particles on a ring. Now, to actually calculate this, we won't go like too much into detail, but it's worth just looking at it. I put the equation here. Basically what you do is first you need to have a symmetry group, okay? So like in this case, we're just sort of considering these like sort of discrete translations around the circle. So we have to specify a function that basically takes a basis state and applies a group action to prepare that basis state from a reference state. So whatever we chose to be the origin. So in the case we were just considering, we actually just use the shift operator that actually we talked about before in terms of like the Weil-Heisenberg group or whatever. So this is just the operator that takes 1, 0, 0, 0 to 0, 1, 0, 0, 0. It takes the latter to 0, 0, 1, shifts everything over. And so if we just start at the 0 state, we can apply it, whatever, I times to go around the circle. Now this, to get from one perspective to another, in the case where we're just dealing, with the particular, they all have the same, all the systems have the same Hilbert space, and there's just like particular symmetry that they have. We can construct a unitary transformation that like does the perspective switch. And so here's sort of like how you construct it. So if you wanted to switch from perspective A to perspective B, you would go over each basis state of the Hilbert space that they all kind of have. And you would construct this operator. So it's identity on A. On B, you have this little thing that basically takes the ith basis state and gives you back G dagger, or like the inverse of the group operation that prepares the ith basis state from the 0 state. So this will basically, in terms of the circle, this will like give you like the state that you give you like counted backwards in the circle. And then you'd apply G dagger to all of the other systems. And then you add up all these operators. There's one for each basis state. And then you do a swap operation between subsystems A and B. And so the net effect of all this is to basically like sort of push B into the reference basis state in such a way that you're kind of like dragging everybody else along with it, okay? And it implements this idea of a coherent change of reference. In other words, if under the change of reference, like from A to B, you go from this psi to this psi. And if under A to B, you go from this phi to that phi, then if you were in a superposition of, oh shit. I'm sorry. Psi phi, right. If you were in a superposition of psi and phi, then you would get a superposition. Like in other words, you can, whereas classically there's just sort of a reference frame switch from one perspective to another. In the quantum case where you can have superpositions, you're kind of imagining for like almost like for every element in the superposition, like all of the different possible like classical states, you apply the reference frame transition to that classical state, but you do like them all because you can have the superposition over all of them. So you're kind of doing like a superposition of, or a kind of a, as I said, coherent change of reference. And so this just implements that. And so, as I say here, this is just that same code, and G is just the shift operator. On the other hand, if we had qubits, what would we do? Well, we would have G would basically be, so we need an operator that can prepare, that's part of this group and prepares the different basis states. So simply, if the reference state is Z plus, then there's two states for a qubit. So G0 would just be identity, you don't need to do anything. And G1 would just be X, because that flips to the other basis state. Now, like if instead the reference state had been like X plus, right? Then, similarly, G0 would be the identity, but then G1 would be Z, because the Z operator would flip X. So let's look at that. Qubit, QRF. Okay, so similarly to before, we have 3 qubits, red, green, and blue. Actually, I'm gonna start from this state. It's easier to see. So yeah, we got red, green, and blue. This is Z plus, facing towards the camera. So everyone sees themselves in the Z plus state, sees themselves, right? So here, red is in Z plus, green is in Z plus, blue is in Z plus. Now, from red's perspective, I've just chosen the starting state where green is in Z minus and blue is in X plus. So what does the same situation look like from green's perspective? In order to do that, as I say, we just have G being, either the identity or X, plug that into the formula, and this, will give you a unitary transformation that takes the quantum state from, red's perspective to green's perspective. Or I could get a unitary transformation that takes me from reds to blues, whatever. So, kind of sensibly, since red is up and green is down, from green's perspective, green is up and red is down. Duh. But, blue similarly is just pointing to the right. The situation becomes more interesting when you consider like what would it be like to be blue, because this is like a little bit different than just like a bunch of points on the sphere and like maybe somebody's like rotated relative to somebody else, because like we're dealing with a qubit, right? And what is a qubit pointing in the X plus direction but a superposition of a qubit pointing in Z plus and Z minus, okay? So the point is that like red and green are both inseparable states. Like he's up, green's down, and blue is in a superposition. But just like we saw in the case of the ring, when we go from try to go into blue's perspective, where blue is in a superposition, then the other guys are going to end up in an entangled superposition. And so that's why you only see the blue arrow here, because red and green actually end up in a maximally entangled state, an entangled superposition. And so they're density matrix is just the maximally mixed state. And so their expected rotation axis is just 0. So that's why they're not here. We could, let's measure, what do we want to measure? Let's just measure blue from red's perspective, see what happens. Okay, so now blue has collapsed to being, Z minus. And so here, both blue and green are Z plus, right? From this perspective, and red's opposite. So, we can look at it, like, what would it look like? Let's evolve. Let's evolve these guys. Let's evolve them in a little circle. So this is kind of interesting. So we're rotating green around, like the y-axis, okay? So this is red's perspective, and let's do this for a long time. So this is from red's perspective. So from red's perspective, green's just rotating around. Now, if we were looking at this from blue's perspective, it's basically the same thing, but like just everything's flipped. So, if here red's up, blue's down, here blue's up, red's down. And if green's rotating in a counterclockwise direction, then here green is rotating in a clockwise direction. But then you can really see what we were talking about before when you consider things from green's perspective. So when green, look at the moments when green is in the same place as the red or the blue. When green and red are the same, this just looks like you'd expect, right? Green and red are in the same place, blue's opposite. And then comes around, now green and blue are in the same place and red is opposite. But these intermediate states, from the perspective of the Z quantization, they're superpositions. And so from green's perspective, when green is pointed in one of these intermediate directions relative to red and blue are in a entangled superposition. And so you see their rotation axes, shrinking and getting bigger because, when, basically they're in pure states when blue and red are, aligned, and they're going to be in mixed states, entangled mixed states, basically, when you're in intermediate directions. So, this is not exactly because we're dealing with qubits and because we're dealing with superposition, this idea that different points on the sphere, superpositions of other points on the sphere, et cetera. This isn't merely a reference frame which would just consist in a rotation.
Matt, can I ask a question?
Mm-hmm.
I apologize. I haven't, heard your entire talk. So maybe you covered this. Maybe this is out of place, but maybe you could help me understand this.
Mm-hmm.
Can't get my head around. The Pauli matrices are all unitary matrices.
Yeah, they're unitary.
Okay. So how do you go from the Z representation to the X representation and make it make sense?
Well, how do you mean? So they're not only unitary, but also Hermitian. And so they each have 2 orthogonal eigenvectors. And so, to go from one perspective, so in that case, right, to express a state that's been expressed in Z in terms of Z eigenstates, right? So it's A plus Z up and B plus Z down. If instead you wanted to express that as a superposition of, say, left and right, along the x-axis, you would just take the inner product of the state, quantized along the z-axis with the 2 x eigenstates.
So if you take the inner product of X and Z, then you should get eigenstates plus and minus 1. Or if you take take the inner product of any direction with Z, you should get plus and minus 1, because if you measure in any direction, you should get either plus or
No.
minus 1. Is that right?
Not quite. So, I mean, you can also like think about it in a more symbolic way, right? Like if you had like, okay, up and down or along the Z direction, okay? And we're in a superposition. Like if you know that it's the case, right? That, you know, what is up arrow in terms of X eigenstates? It's just a superposition of left and right. And similarly, you know, what is down arrow? It's just left minus right, okay? So then, you know, you can take the inner product or like whatever, like I was saying, but like if you like to work more like symbolically, right? Like you can just substitute these in. Like here's down arrow. Here's right arrow, or up arrow rather. And you get that, right? And then,
But bottom line, whatever direction, and it doesn't have to be an orthogonal direction, whatever direction you measure in, it's got to be plus 1 or minus 1.
well, we're not really talking, well, what do you mean? So it's like those correspond to these basis states.
Right.
That's what you know.
But even if you measure at an angle, it still has to be, if you haven't already measured, it still has to be the plus that direction or minus that direction. I guess the math all works out, whatever, regardless of what angle, even if the angle is not orthogonal to the z-axis. I mean, physically.
Okay, so like you can, like you have your XYZ operators, like you can just like rotate those and get like, you know, to describe like measurements in any direction. And like, in fact, like, you know, we would use this in spheres a lot. Like you can take like any 2x2 Hermitian matrix, which represents an observable of a qubit. Its two eigenstates will correspond to antipodal points on the sphere.
Right.
So, you know, you can describe a qubit as a superposition of any two opposite points on the sphere. Those could be Z plus and Z down. They could be X plus and X down. They could be anything.
So if you rotate any of the Pauli matrices with, let's say, just a simple rotation matrix, you should get the eigenstates have to be plus or minus 1.
Well, you mean the eigenvalues?
The eigenvalues have to be plus or
Yeah,
minus.
the eigenvalues will, yeah, they'll, sure.
And the math, I assume the matrix algebra has to work out to that.
Yeah, I mean, it's just a rotation. So you figure the eigenvalues are going to stay the same, I guess. I mean, it's like, and again, I mean, you'd use the Pauli matrices to implement that rotation, right?
But if you rate, let's say you start with the z-axis and you rotate the Z Pauli matrix into the x-axis, you know, by multiplying by, you know, rotation matrix, do you get the X Pauli matrix?
Well, let's try it.
You get, I mean, you're going from real eigenvalues to imaginary eigenvalues, or let's say to Y. You're going to Y.
No, because so you're probably thinking of using like the normal 3x3 rotation matrices, but you know you would use the
or 2x2.
Yeah, right. But so for sure, so you know they're still going to be complex or whatever. So
but not necessarily. I mean,
what you want to do, you want to take X.
It could be trigonometric. You take The Z matrix, which is real eigenvalues, you rotate it, you know, sine, whatever it is, cosine, sine, minus sine, cosine, which are real numbers. Let's say you're rotating it into the Y, you get
Well, because
imaginary eigenvalues.
no, because you know, I think you're thinking of the like the 3x3 orthogonal matrices that are like full of the sines and the cosines and stuff. To do the rotations here, recall that you exponentiate the Pauli matrices to rotate around that axis, right? So do -1j times, you know, x times, you know, whatever angle I want to rotate around.
So you're doing e to the I theta matrices rather than
Yeah.
sines and cosines. So that's where you get the imaginary eigenvalues.
Yeah, so like let's so I think we want to divide by 4 because you know, these are the Pauli matrices that have eigenvalues 1 and 2. So that's like a rotation here. So like suppose we had our Y matrix. We rotated around the x-axis. We want to get the Z matrix. I mean, yeah, like if we get our
Yeah, let's do Y because
it should work. It should
Y
work.
has imaginary.
R times X times R dot dag. So what is print Q? Well, that didn't work at all. Oh, I meant Y here. That's what I wanted. Yeah. There it is. Yeah, so, okay, so we rotated X into Z, right? So here's Z, okay? We started off with the X matrix. We took the Y Pauli and we exponentiated it. I times pi over 4 times Y. Now, when you transform operators, recall that you multiply by your unitary on the one side and multiply by the adjoint of the unitary on the other side. And so we start out with X, rotate it basically a quarter, you know, we start off in X, rotate like a quarter turn, and we end up with Z. So there you go.
But when you do it with Y, I mean, Y has those I values in it. X and Z have real values.
That's true.
Y,
But you know, they all have the same eigenvalues. X,
Yeah.
Y, and Z all have the same, you know, they all have eigenvalues -1 and 1.
yeah,
It's right
yeah.
that, you
So
know,
if you use the e to the I pi over 4, then the eigenvalues have to come out to plus and minus 1, regardless. Yeah. Okay.
yeah. And remember, it's like this does a pi over 2 rotation, but you add the extra factor of a half because of this convention that we've used for the Pauli matrices. Like, for example, like if you use JMAT, this function to get your rotation matrices.
Well, if they're orthogonal, then it's
multiply by half.
if they're orthogonal, then they differ by 90 degrees, pi over 4. Oh, I'm sorry. No, it's pi over. I'm sorry, it's pi over 2.
You know, this is just because of a convention by which the whether you've decided that the Pauli matrices are going to have eigenvalues 1 and -1, or a half and -1/2.
Oh, okay. So the half is outside of the matrix. Okay, yeah.
Well, yeah, so it's a question of, do you put the half in the matrix or keep it outside?
Well, the rotation is e to the pi over 2, but the half is outside of the matrix. But yeah, well,
Yeah,
okay.
yeah. So like if we did QT JMAT 1/2 Y, that would give
Their half spin.
So yeah, we've stuffed the 1/2 in the matrix instead, and so then we just use like the normal angle that we would want. Just rotate 90 degrees.
Hey, thanks. Thank you.
Sure. Yeah. So, yeah, qubits. Well, what is this? Oh yeah, this one is, okay, so from the Z perspective, Z's up, but blue and green were in like the, actually for fun, let's do it in like the, whatever, the state where they're always anti-correlated. So here, as I say, the partial states for, that state are like maximally mixed. So in this representation, you don't see the green and the blue arrows, they're just length 0 and red's Z plus. But if you were green, remember from red's perspective, green and blue are, in this, if one's up, the other one's down. And so indeed, if you were green, then blue would be opposite. If you were blue, green would be opposite. And consequently, red would be in a superposition of being up and down, AKA pointed in one of the X directions. So if from red's perspective, green and blue are maximally entangled, from green and blue's perspective, red's just in a superposition, and vice versa. Like if green sees red in a superposition, then red would see blue and green in an entangled superposition. That's just sort of like how this whole formalism works. And then the last thing I just wanted to show you is like, we can do the same thing, but like in a different basis. So for example, what if we had our reference state be the X basis? So, it suffices for our little group function that, prepares any of the basis states using one of the group elements from some reference state. It suffices to use, if we're just in the basis state already, this identity, and if we're in the other state, Z, because Z flips X eigenstates between each other. And we use the X eigenvectors as the basis states, as I say. So when you look at this, it's like we start off in the state where red is, pointing in the X direction, and blue is also pointed in the X direction, and Z is in the, green is in the Z direction, Z minus direction. And does this make sense? Yeah, I guess it does. So like green here is in the basis state. This is a superposition with respect to these guys. So these guys are an entangled superposition relative to this guy. And so we can. So, so basically to play this game, you can, you have a bunch of quantum systems. They're all like, one precondition is that they kind of like have a symmetry group in common, right? Like they're all qubits or they're all particles on a line or whatever. And so you need like a way of basically, constructing the elements of the symmetry group that can prepare the different basis states. And you choose which basis states that you care about, and then you're good to go. Now you can imagine generalizing it, like it could have been something else, right? Like we could have used, whatever, some other quantum system, some other group, and done the same thing, right? Ultimately, if you cared about much more complicated physics, you'd want to be like the group elements from the Poincare group and whatever, get all fancy. But interesting questions arise when you sort of think about like, what if the systems sort of have different symmetry groups and other things, and so you sort of worry about whether the transformations are unitary or not. And there's all this sort of like interesting literature about this kind of thing. Some of which I provide here. So they look at some other examples, some other simple examples, And then you can also look at like, how do the form of the laws themselves change under these reference frames, reference switches, right? Like in this case, we just get a unitary matrix back that takes us from one reference frame to another, but we could transform operators as well using that unitary. And so you could wonder about like, Einstein's principle of general covariance, like under these reference frame switches, do the forms of the laws like, remain the same? And, people have been working on that kind of stuff. And, I think as I mentioned when we talked about it initially, there's different senses about quantum reference frames, whether, you can approach it from an operational perspective and be like, like it's not so much that you're gonna like switch reference frames, but you only can measure the spin of something or whatever relative to some other quantum system. So like you're only allowed to do sort of operations that like or like relational or whatever. Then there's this sort of perspective where you're like, it asks you kind of imaginatively, like to literally sort of be like, well, if you were that quantum system, what would the quantum state of the rest of the world be like? And I think that like, it's an interesting question how you would test that, right? Because like, you can't like act, I mean, it's an interesting question. But certainly like in that case I was talking about where it had the sort of practical value, you have some particles speeding along in a superposition of momentum states, and you want to find a reference frame switch that would take it to the rest frame in order to define the spin. How would you do that if you can't use a classical change of reference, because that would take, moving with this momentum to maybe being at rest, but you're in a superposition of different momentum modes. And so this idea of kind of like doing all of the possible classical reference frame switches, in a sense, for each kind of one on each basis state of, this potentially superposed state, is kind of an interesting one. And of course, I mean, this sort of, it's an open question for me, how this way of thinking plays with the different interpretations of quantum mechanics, what to make of the many worlds, right? Like if the many worlds have to do with how things are entangled in blah, 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 blah. Well, here's like a sort of a whole nother take on that. If you're a Bohmian, what do you make of this? If you're a cubist, what do you make of this? I don't have any real answers to any of those questions, but I think it's it's sort of interesting. I mean, you sort of
Can I say something?
the basic sense. But.
Spin is not Lorentz invariant. I mean, spin is essentially an internal characteristic, and it only comes to light when you apply an external magnetic field. That's the only way to measure it, with an external magnetic field, which changes the whole picture, the whole quantum picture, because you're introducing the rest of the universe, so to speak, when you make the measurements.
Actually, the argument goes the other way around. It's Lorentz invariant, and when you break this Lorentz invariance by imposing external magnetic fields, then you can see the spin.
But that's a philosophical perspective, isn't it?
Well, no, because I mean the Lorentz invariance says that any observer that is Lorenzly equivalent to another observer would have the same kind of understanding of the data. Doesn't matter what is going on.
Like that, yeah, I mean that should make sense to you, Michael, in the sense that, I mean, you're often saying like, you got to use, quantum field theory or whatever. And we're often talking about, it's like, well, in order to get, like the Dirac theory of the electron or whatever, like you have to include spin in order to actually like represent the transformations.
So then the spin is Lorentz invariant as your mentor.
When you say spin, right, it's like the spin axis
Yeah.
might not be
Well,
Lorentz invariant.
I mean, the thing is that what's invariant is if you have an object that has a spin and you're not messing up with this object, then you can choose Lorentz equivalent frames because this is whatever you want to choose.
Right.
But this has nothing to do with how this thing is carrying its spin. So basically your formulation would be made in a way that by changing from one frame to another through Lorentz transformations, you will find that the records of whatever observations were made by different Lorentz equivalent observers would start matching each other. I mean, it doesn't mean that, like what is up is for some down or left or right. It depends on the viewpoint of the observer. But the symmetry is that saying if you go through different observers, basically this doesn't change the state of the particle because it's not bound to the observer. Now, of course, in quantum mechanics, it's a little bit different because when you do a measurement, you start interfering with the state of the system. But still, quantum field theory is built on the presumption that you have to build a Lorentz invariant theory, which means that your theory would be able to account for different observation by different Lorentz equivalent observers.
Thank you.
Yeah.
Yeah, definitely. Like, had you heard about this sort of work on quantum reference frames? You know, it's
I heard, but I haven't really dive into it because I'm busy with other things.
Sure.
Basically, I think this is kind of makes sense of what, in the sense that like the Everettian people would kind of argue, saying that if I'm in superposition, then everybody else is in a superposition and things like this. And all this is possible just because you allow superposition. The interesting thing is that Penrose is saying that maybe gravity is messing up this capability of superposition and basically collapses the wave function effectively.
yeah, you know, I mean ultimately like these reference frame switches, I mean, they end up just being, at least in this case, unitary transformations. So
Yeah.
like it really does assume, you know, like nothing more than your usual quantum mechanics. Like if you're just allowed to do a unitary, then you're fine.
But be aware that it's actually built in because of the technology that we already know. Because in Galilean symmetry systems, you apply Galilean transformations and you have the Galilean group of transformations. Then you go to a Lorentz group of transformations. And now you have to put yourself, it's pretty much the same thing what was happening like maybe 2 centuries ago when people were trying to figure out what is happening when I'm changing coordinates. And then they discovered the Coriolis force and all these kind of effects that you have due to different coordinates. I mean, what coordinate system you picked. Now, quantum mechanically, this transformation that's classically kind of now considered to be understood are mapped now to a unitary transformation because you're working in a Hilbert space. So naturally, you're demanding that the transformations upon changing observers has to be matched with unitary transformation in the whole framework of operators that you're using in states. And the whole quantum mechanics is built with this kind of presumption that it has to actually be unitarily equivalent. I know that there are people who are looking at something which is deviating from the Hermitian requirement. Basically, you know, that there is a CPT theorem and also the Hermitian operators that you want for observers. So some people said, well, maybe I don't need to have Hermitian operators. All I want is, I think they were talking about PT symmetry. So parity time symmetric operators. And then they were claiming that this can result in actually meaningful quantum theory in operators, again, that you can relate. But my feeling, as far as I had opportunity to look into it in discussions, it's just a question of how do you define your metric and Hermitian structure, basically. I haven't seen, but I would suspect that eventually somebody would come with a theorem saying, oh, these PT symmetric models, upon proper definition of their metric space, will turn out to be Hermitian operators again within these things. Because remember that there is a different ways you can impose a metric structure on your space. But we usually pick the metric structure that is consistent with the observations, I mean, what makes things kind of consistent with our previous knowledge.
Sure.
Oh.
Well, yeah,
So
like
that's
where you're
the
just
same thing. Yeah.
well, when you're just respecting PT symmetry, like if you were just working with like, you know, finite dimensional matrices, like what symmetries would the matrix have?
What do you mean? Well,
Well, if like a
oh,
Hermitian
then
matrix is, you know, equal
yes.
to
Then you have complex conjugates and transposition, but often the complex conjugate actually translates into charge conjugation.
right.
Effectively. But it depends. You have to look at what are the operators in your theory.
Yeah, yeah.
How do you define your model space? What does it mean, orthogonal vectors and things like this? Now, the good thing is that the thing that you were talking before about the positive value operators, this deviates from the usual orthogonal basis consideration because, again, choice of orthogonal basis is just choice of convenience. In principle, nature shouldn't care whether your basis is orthogonal or not. But it's useful for us because once in a particular state, you can say, here the amplitude is then the probability to be in this state. And then I have to sum up all this amplitude to get one because they are orthogonal, so I cannot have overlap. And the moment you're allowed to have overlap, you have a headaches to figure out, I mean, how do you interpret probabilities?
Yeah. Well, I mean, the qubit stuff seems to have a, you know, a nice interpretation of the probabilities, but it's like, you know, the really unfamiliar thing is like you make a measurement, you get an outcome, but it's not at all guaranteed that if you do that exact same measurement a second time, you'll get the same outcome. In other words, you'll just get the previous outcome with like the highest probability. But of course, because it's not an orthogonal basis, you know, there's like non-zero chance that you'll get one of the others.
But you see that the thing is that I don't know how they do it experimentally, because in physical reality, I mean, this is subtraction, where, I mean, between two measurements, you don't allow any interaction with the environment.
Sure.
But in reality, I mean, you do have it, and if that's the case, then you're not guaranteed immediately after two measurements that you'll get the same results because intermediate kind of step in external interaction may change things.
For sure, for sure.
Yeah, can I make two comments? In the real universe, putting mathematics aside, in the real universe, as far as we know, only CPT symmetry is guaranteed. PT, CT, CP, P or C, these are not guaranteed. Only CPT is guaranteed. Also, if an operator is not Hermitian, then you don't have a guarantee of real eigenvalues.
Right. But the thing is that, like the theories that I mentioned, they find a way because it may not be Hermitian with respect to the traditional Hermitian definition, but then you can still actually extract real numbers somehow. And that's related to actually a different type of choice of orthogonal, because the Hermicity is defined how the operator acts and what is its dual space. I mean, basically, you have states and dual states. That these dual states actually are the things you can consider the outcome of a measurement. I mean, like the projector. I mean, the dual vector is the one that is evaluating the state. So these are the linear functionals. So anything that is linear with respect to the state and gives you a number.
But but then how can you justify something like PT invariance? Only CPT.
Well, that's what I said. I mean, the thing is that it's interesting construction that, and I suggest you can Google and see the papers. I mean, of course, that they're having hard time. I mean, basically because people say, well, I don't know why you should do that when we have all this. But I think in general, it's good to explore other options until somebody figures out and say, yeah, these are all kind of equivalent to a weird metric structure of your space. And once they figure it out, then I mean, it doesn't become so interesting. But until then, I mean, they can try to make predictions where you can actually have experiment and observe something that according to standard CPT, symmetry, and kind of Hermicity calculation, you get one number, and according to their calculation with PT symmetric Hamiltonian, you get a different number. And then you do the experiment, and that's what it tells you, right?
Yeah, yeah, very interesting.
Until you do an experiment that violates that.
Right. Unfortunately, most of the time, I mean, people are very busy putting theories, but they don't think about how they can actually verify this theory with experiments. They just say, "Oh, it's obvious. I mean, just let the experimentalists do it," and then the experimentalists that they cannot figure it out. I mean, they don't believe in it, and so why should I waste my time on that, and so on.
Well,
Yeah.
CP symmetry was assumed to be true, but then, of course, it was disproven.
Right. So the thing is that these are the traditional framework where you can have the experiments and say, well, now you can let go of CP symmetry and you just go to CPT. Of course, the CPT is related to the Lorentz invariance, and that's why there's a lot of well, not a lot, but you can see, I mean, basically depends if you're in the circle of people who are looking for Lorentz invariance violations, symmetry violations, then you'll see that there's a lot of people working in there. And basically that there are people who get grants to do research on it and do experiments to confirm that there's no Lorentz invariance violations. But again, you never know. I mean,
why would anyone expect a Lorentz invariance violation?
Why?
Well, there are different reasons. I mean, people would think that somehow this might come from the problem that Planck scale, if it's kind of universal, it's kind of weird because you cannot get to the Planck scale if you do different boosts and things like this on the Poincare group, which gets you the usual commutation relations and particles. Basically, it's quite weird that you have a Planck scale where something would be different. And so people would just try to fix this, like double general relativity or double special relativity, where they would consider that when you're about to get this kind of breaking of the Lorentz symmetry, something would pop up and things like that. I agree. For me personally, local Lorentz symmetry should be always valid. I don't know how do you validate it actually globally, because globally, I mean, this is related to the fact that general relativity is, I mean, from one point of view, you can see there is a curvature, and you're not guaranteed that the space is flat. I mean, locally it's flat, but when you get to to a black hole, that's a lot of curved space there. And the question is then, what's going on? I mean, how can I have a Lorentz invariance? I mean, the time translation there would definitely fail, and then a bunch of other translations that they cannot go to infinity, right? Then there will be some kind of something going on.
But if you don't have Lorentz invariance, don't you run the risk of violating causality?
Right, that's correct. I mean, the thing is that I think that's the strongest case. But I don't know if you come across these theories like retrocausality, which are trying to explain some of the behavior in quantum mechanics, where the things are not only depending on your initial conditions, but on your final conditions. So basically, your experiment is predetermining what were the initial condition for your experiment to do. So it's kind of retrocausality in a sense. It's not really, I mean, violating causality, but in a weird way, quantum mechanics allows the future to tell the past what their state should be so that it's consistent.
No, but to
I always
answer,
felt like that the string diagrams always make that, or like encourage that like interpretation. Like when you think about the teleportation diagram, like you see, a state go up, and then you see, it's like two entangled particles go up, but then there's this measurement. And so it looks like the particle like hits the measurement, goes backwards in time, goes across the entangled state, and comes out the other side.
no, but to answer Moshe's question, entanglement does not conform to Lorentz invariance, but it certainly does conform to causality. So you can have causality without Lorentz invariance.
Well, these are all coming to like the Bell's theorems and different variations. I mean, when people were doing de Broglie and pilot wave and all these kind of things, well, what do you have to give up on your theory? And it seems that, I mean, most people are willing to give up locality rather than all the other things.
Yeah, well, pilot wave and Bohm theory, de Broglie and Bohm involve entanglement. The quantum potential is an entanglement that evolves the system, but it is still causal. It is not acausal.
Right, yeah.
Yeah, it's always fascinating to me, the trade-offs in the interpretations. Like, as you say, it's like, do you give up locality? Do you give up realism?
Yeah.
You get to pick.
Well, I mean, I listened to interesting iPod podcasts a while ago. Basically, they said that they set up to try to figure out which interpretation would kind of fail, and they were trying to really hoping that the pilot wave would fail. And they were kind of very interesting, complicated, convoluted quantum mechanical models where you have the building on top of the Schrodinger cat and what was the other one? The Schrodinger's friend.
Oh, Victor's friend. Yeah.
Yeah. And basically that's what I got from that was that at the end, it turned out that there were two that kind of still were hanging out. I mean, that didn't run into problems was like the superdeterminism, which is one of the things that, I mean, Bell is saying it could be. We don't like it, but it could be. And the other one was the Bohmian, because basically they say, well, as soon as you're part of the system, it's difficult to say what's going on. I mean, you have to get out of the system, but you cannot get out of the system because you're part of the system. So,
what is superdeterminism?
Oh, that's like what David was talking about at your meetup a couple weeks ago. Just the idea that even your choice of what to measure is determined. I mean, I think about it like if Conway's, he's got that free will theorem that says something like, you assume relativity entanglement, whatever, and you say something like, to the extent that the experimenters have the freedom to choose what to measure, then nature has just as much freedom to respond with an outcome. And but the loophole there is like, well, what if we have no freedom whatsoever to choose what to measure? Then nature has no freedom to respond.
Yeah.
Everything.
So the
Well,
thing is
this
that
is-
it's very sad, because then you're thinking that you're making a free choice, but
Yeah.
basically it says no, I mean, you're just following the flow. And that's philosophically, people say, oh, it's bad, because then everybody will say, oh, I cannot do anything, and it's it's beyond my control.
Yeah, Matt, sorry to disappoint you, Matt, but there is no free will. But what I wanted to say is that where pilot wave theory or Bohm theory fails is the same place where Copenhagen fails. The fact that they are both non-relativistic theories. The true theory is a quantum field theory, a relativistic theory. Other than that, Bohm, for non-relativistic phenomena, Bohm is far superior. That's my own personal opinion.
Well, like
Yeah.
I mean, to push back against your little free will comment, though, I think that for physics, I think the relevant thing isn't like, do we have free will? I mean, that's something that humans care about.
Sure it is.
It's more like, can we regard like what's going on over here as separate from what's going on over there?
When I say, look, I was being
Right.
facetious, but what I meant by free will implies non-determinism. If you believe in determinism, then there's no free will. What comes next
I'm
is what
aware.
happened before.
Hell yeah, exactly.
See, you like probabilities, Matt, so probability allows you to believe in free will. Once you accept determinism, there's no free will anymore.
Yeah, I mean, I am open to determinism. I mean, I find no compelling reason to believe it. But I think, as sort of like Vesely was pointing out, like, I think once you allow non-locality, the question becomes like, how do you define, what is one thing and what is another thing? Like, in order to sort of speak sensibly about it and sort of, do
No,
science.
no, but again, entanglement implies non-locality, but
It does.
non-locality does
does
not
not. No, it doesn't.
imply a
No,
causality.
we were just talking about that, right? Bell's
Yeah.
theorem presents you a fork in the road. You can give up locality. You can give up realism. You can give up some other stuff. The one doesn't apply to the other. There's like various positions you can take on this issue.
But you never give up causality. And what I'm saying is that Copenhagen implies that you can give up causality, that there's probabilities, that there's not determinism.
I feel
Causality means determinism. And
Oh, no.
why
No,
separate concept.
There are two things. I mean, causality means that there's cause and effect. I mean, basically, for something to happen, something has to cause it.
Yes.
But the thing is that this doesn't mean determinism, because, for example, rolling a dice is actually cause and effect. I mean, you have to roll the dice to see actually something coming out. If you're not rolling a dice, it's not gonna give you a random number between 1 and 6, right?
No, but it's not, with all respect, it's not random. If you know the initial conditions, which we don't know, if you know the initial conditions, then there's no probability when you roll the dice or any other operation. It's just that we do not know the initial conditions. We don't know how to measure it. This is Bohm's theory.
Right, but the thing is that what you can say is, not knowing the initial condition, you can say that there's external factors that would just come, and you don't know all the possible external factors that would interfere with your process.
Yes, we don't know
Yeah.
them, but they
Yeah.
exist. They
Right.
exist nevertheless. Nature knows them.
Right, and because the thing is that then you can understand causality by looking at simple, chains, and then you can say that that's all it is. There is no like hidden chain that I cannot see. And then in this sense, you're not giving up causality, but determinism, basically, it's even for probabilistic theory. I also think it's deterministic as long as you can compute something. Of course, there's the issue when you run into kind of divergences, like saying, oh, how do I compute this, something that blows out? And of course, they figured out how to fix these problems too. So to me, if you can compute something and you can put it into experiment, this is kind of very good determinism.
Okay, but nature, computing is a human, it's a human endeavor. It's a human operation. Nature does not compute. Nature just follows its own laws.
Right, but if nature is equivalent actually mathematics, I mean, just computing is just our way to talk about it, but nature is just following some of the rules of mathematics that we haven't described, completely uncovered yet, or maybe we haven't just admitted that we understand them and it's nature is basically mathematics and that's it.
Right, and then when we discover the ultimate way of computing, then we will see it is deterministic.
I
My
mean,
opinion, my opinion.
yeah, I mean, I think, you know, you often paint me as like a believer in free will. Maybe I do, maybe I don't. But like, I feel like at a more deeper metaphysical level, whatever the truth is, I think that our human concepts fail to grasp it. Like the very ambiguity between Bohmian mechanics, Copenhagen, many worlds, cubism, whatever, seems to me suggest that like nature is like just not productively looked at in terms of like it's deterministic or it's not deterministic. Like, what is it about human beings that like we want there to be like a line? That
No,
you
but Matt,
deterministic.
there's
It's
only
not.
one, Matt, there's only one real theory. There's only one real theory. The others are all hypotheses. And we don't know which is
I
the
don't
real
know.
one.
That seems to me an assumption. Like, just like there are many, you know, laws on the planet of human laws that apply differently in different places, I don't think there's really any necessary reason to assume that the laws are the same everywhere. We believe that, generally speaking, today because there's empirical evidence, right? Because like we looked up at the night sky and we found that the laws of general relativity and laws of quantum mechanics that allows us to predict the, you know, frequencies of light and so forth look like they're satisfied, you know, up in the galaxies. But that was, you know, an open empirical question before that point. Like the assumption that the laws are the same for all time and for everywhere is like just that. Like it's like a working hypothesis.
That's not what I said. The laws, I grant, the laws could change. They probably do change. But the point is that if nature were not deterministic, if nature were probabilistic, then we would live in a chaotic universe where there's no chance of predicting anything.
You often say that, but like I don't know why it's like it's so black or white. I mean, could it be like in the middle? I mean, I don't know.
Well, because nature, you're confusing math with physics. Nature doesn't do math. Math is an invention of the human mind in a very weak attempt to try to explain to ourselves what nature is doing. Nature doesn't do a mathematical calculation. Nature just acts according to prescribed law. And we don't know how to describe that exactly.
But couldn't it be just the other way around, that like nature acts in a kind of lawless way at some level, and we're
Well,
the
then we would live in
apply
chaos.
laws to it?
We
No, I
would
mean,
live in a
like,
completely chaotic universe. That's not the universe we live in.
but we do in so many ways. I mean, you know, it takes billions of years of evolution to create the regularities that we rely on every day. I mean, so much of human life is like the creation of laws and habits that allow, you know, like us to keep the lawlessness and anarchy at bay. I mean, I don't know.
I think you answered my question. I think you confirmed what I said. Whether it's evolution or, you know, a natural law or whatever you want to call it, it's not chaos.
Well, but the thing is that what you have to take the lesson from quantum mechanics is that when you go to the path integral interpretation is you have all these classical possible paths very well determined, and now you allow that all this would happen. And people do talk like this and say, well, what if nature is such that all possible theories and everything is possible?
No, but again, this is mathematics. This is not physics. You got to make the distinction between how we try to describe what's going on, and we use mathematics, which is a very inexact tool, versus what actually is going on.
But
Right.
quantum mechanics fundamentally is statistics. I mean, according no matter what you call it, the quantum mechanics, fundamentally the concept is, the everything happening according to statistics. There's no, it's not deterministic. Only deterministic part only for the probability, how the probability, how the wave function evolves. That part kind of deterministic, but what underneath the wave function is statistics.
But the statistics starts at the initial conditions. The
Well,
initial
wait.
conditions are a real
This is
statistical
the
distributions.
people observe with many experiments. It's not something you simply believe or not.
No.
Because the
But
observation, right? It's the quantum mechanics built on experimental observations, many observations. Not
but
simply you believe or not. Yeah.
but the problem we have is that people confuse a probability with a statistical distribution. In the real world, we
probability
have,
distribution it's not deterministic.
Yeah, well, you should know that Michael, who is arguing for determinism here, like he loves Bohmian mechanics, and there are many attempts to formulate deterministic versions of quantum mechanics at the cost of sacrificing locality, and also making it that the results of measurements are contextual in a way that sort of elides their semantic meaning. In other words, the result of a spin measurement would depend on contingent details of the location of the particle and the orientation of the apparatus in ways that don't seem to have anything to do with spin.
but
So
Matt,
you
all
can
quantum,
twist, the theory kind of into a knot, and you can create like a sort of a deterministic version of it at, some cost. But it can be done, whatever.
Matt, all quantum physics, whatever theory you believe in, violates locality. It's called entanglement. Entanglement violates locality. And
No,
that's a real phenomenon. That's not even theoretical.
there's other interpretations of that. Again, in both many worlds and also in cubism, for example, it's completely local.
Well, again, many worlds is an outrageous. It's outrageous to say that that's physics. That's fantasy.
Really?
There's no way to test it. There's no way to test it, and therefore it's not physics.
Okay, well, again, I don't want to get into that argument again, just because you really can say the same thing about Bohmian mechanics. Like, it's
No, Bohmian mechanics is
to the same
testable.
extent. I mean, we have to agree about that, right? It's like you get the same predictions. In many worlds, it's like the correlations just are because you ended up in one branch over another. No non-local forces, no faster than light signaling. And in cubism, it's more like the observer like brings the correlations like sort of like with them. Like, in other words, they would say like, all right, you measure 1/2 of an entangled particle, and a Copenhagenist would say, oh, that just like automatically means that like this guy over here collapses to a correlated state. But the cubist would be like, well, you don't really know that, right? Because like you actually have to go over there and check and make a measurement yourself, with which elicits a active creation. And so it's not strictly non-local, because like to actually confirm that it was there, to kind of bring it into existence, you had to go from A to B.
But Copenhagen also violates unitarity. Bohm, and I would say even many worlds, does not violate unitarity. If you believe in unitarity in physics, then Copenhagen is complete nonsense, because wave function collapse violates unitarity. It's a discontinuity, a mathematical and a physical.
You have to be very careful how you present it. What Copenhagen says is that the evolution of the wave function is unitary. When it collapses, all bets are off. Copenhagen doesn't claim that the collapse is unitary.
Well, yeah, that's why it's wrong. That's why it's wrong,
Measurements, the evolution is unitary.
That's why it's wrong, because as far as we know, physics is completely unitary, whether it's classical or quantum. And whenever you have a mathematical discontinuity, it means your theory is wrong. Your physical theory is wrong.
And it's not the only interpretation. Like, especially like if you go back and read that like Wigner essay or whatever, right? it's like there's a kind of relational perspective being proposed, whereby it's like, from a third person perspective, what looks to you like a discontinuity, like a collapse, is unitary, is just some entanglement between you and another.
How is that? That's not even what Copenhagen claims. It claims that you have unitarity between collapses. But what about the collapses themselves?
Right. So yeah, like I guess in the way that you're using Copenhagen, yeah, that's not strictly the Copenhagen interpretation. I'm just saying, I mean, even people associated with the Copenhagen interpretation, like often, tried to posit a kind of more like relative point of view or a relational point of view, whereby like maybe one, you perceive a collapse, but someone else, sees it as unitary.
Well, I believe in objective.
Again, I would just want to point out though, like Copenhagen, I guess like a lot of bad press. I mean, I think it's better to use the phrase.
Deservedly so.
No, absolutely not. That's my problem. It's like, we should use the phrase textbook quantum mechanics for what we're talking about. Like, in other words, textbook quantum mechanics says you have a state function, you have unitary evolution governed by the Schrodinger equation. When you make a measurement, there's a collapse. Like, that's what we mean, like the axioms that you find in the textbook. What the Copenhagenists were talking about is something that like we don't often talk about very much. I mean, they were like super operational, super kind of positivistic, super like, we are afraid to make definite statements about stuff at the micro world. We're going to make sure to do everything with reference to big, bulky apparatuses and what we can write in our logbooks, and use, classical language in this very delicate way in order to describe this great unknown that's happening in the quantum world. Like, that to me is what really Copenhagen is about. Like, how do you, forge a path of a sort of really undefined metaphysics at the
and this is
classical physics is collapsing around you. That's when you read Niels Bohr and all these other guys, it's like it's much more interesting than just like
no, but interesting does not make it interesting. Doesn't make it real. If you go back to the history of quantum mechanics, when de Broglie came up with the wave particle duality, Schrodinger said, well, if a particle is a wave, then let's write a wave equation. And then when he solved the wave equation, he found out that his solution did not correspond to physical reality. So Born came up with his Born rule, for which there is no logical basis. Born came up with a rule to match.
It's so fucking what? Like, I don't understand.
There was a stumbling block.
People discover things. Like, I don't see how that should make any difference.
There's no consistency. There's no consistency in the theory. There's no logic to the Born.
I have a question for you.
Yeah.
Have you read the essays of Niels Bohr, Werner Heisenberg, and Schrodinger? Like, have you actually read their books?
Okay, let me tell you something.
Because I have.
I've read about de Broglie. I've read about de Broglie and how they were shot down. Niels Bohr, once he achieved his exalted status, and Wolfgang Pauli,
like repeating gossip, like physics, like
they didn't want to challenge.
Like,
one moment, Matthew. Since you read those books, tell us what kind of insight you got from those books. I'm really curious. What can you share with us?
They were promoting their own theory.
No, I want to hear it from Matthew. He read the book.
Okay,
I know what Niels Bohr said.
There's a lot of, there's not like just like one thing, obviously.
Niels Bohr said, shut up and calculate. You don't have to know.
No, really, he didn't. That was David Merman, apparently. But
we don't really know who said it.
I think it was Landau.
Or maybe it was Landau.
Who was it?
Many people.
Landau.
Many people. Is he related?
Landau
to
and Lipschitz.
Well, some people attribute it to Feynman, but it wasn't. It was predated Feynman.
Matthew, go ahead.
Go ahead.
Okay, I don't have like a very specific thing, but like I think, and they're different from each other. Like, I find Heisenberg's writing super interesting to me because it's very, it's very philosophical. Like, it's very steeped in like trying to understand, what's happening in physics, like in terms of like the long arc of like Western philosophy. So like he's going back, like he's quoting Descartes, he's quoting Kant, he's quoting all these people. Like he's trying to understand what's going on in like the broader framework of like the philosophers, which is sort of interesting to me.
None of them were physicists.
Well, some of them were. I mean, especially in that time. I mean, the Cartesian plane, have you heard of it?
I heard of it.
Descartes was a fucking physicist. He most absolutely was.
Hey, my mother is listening in on this. Watch your language.
Oh.
That's okay.
I mean, Descartes had some really cool views. I mean, he had this sort of like vortex theory of like the solar system. And like,
But he didn't know about curved space.
I don't think he knew about curved space. I think that's true. But so, you know, and what is the book? I probably should not try to look it up right now. But I seem to recall there was one particular book of Heisenberg's. That I really
That's a curious, Matthew. What's your background?
Well, I've been a lifelong programmer. My sort of educational background was originally in literature. But now I think about quantum mechanics all day. And, you know, gonna go to, you know, applying to grad schools and stuff.
Oh, I see.
The
Michael, what are you?
Are you disappointed? Let's see here.
Michael, what's your background?
Oh, maybe he went to the bathroom. Okay, well, not to waste too much time on this, I'll probably try to send a link to the
Yeah, you know, quantum mechanics is pretty counterintuitive. It's not something easy to understand. Yeah,
that's for sure. Yeah.
I mean, unless you learn, you know, rigorously through the textbook and doing some experiment by yourself, and you really observe the weirdness of that, then you don't believe that. And it's really, you know, counterintuitive, different from our daily experience. Yeah.
Yeah, I mean, it gets at, you know, the point I was going to make about like, you know, if Heisenberg, you know, is constantly trying to sort of fit things into, you know, that sort of philosophical framework. You know, Niels Bohr is kind of the philosopher too, but he's like sort of, whereas I think, you know, Heisenberg's, you know, story, right, is he, you know, he has like hay fever.
But then, you know, philosophy is mostly argument, right? A way to argue. And, you know, physics is physics. Physics is just an experiment. And the math, you know, math is basically, math by itself, there's no correct or wrong. Mathematics basically, you know, you assume and her certain hypothesis, then you think of, oh, this math, you know, could be a good model for this. Then you start derivation. As so long as, you know, math is the purpose to maintain the self-consistency. You know,
model is the key word here. Model is the key word.
Mathematics is always, everything proven is relative to
any model has a range of applicable. You know, beyond that range, that means that model doesn't work.
Philosophy and mathematics are human endeavors. Nature, quite honestly, doesn't give a damn about philosophy and mathematics.
Sometimes you're right.
Nature has laws.
And
nature.
Yet.
You know, when you talk about law, actually, the law, you are talking about the human's recognition, you know, the law, right?
No, I'm talking about the fact that we have limited intellect. This is a very egocentric a philosophy that we can explain everything. And maybe we can, but we haven't been able to up until now.
Yeah, you mean, I mean, you do your best, right?
You do your best, but that doesn't necessarily conform with reality. It's just our way of explaining to ourselves.
We know it does not conform with reality.
It's our way of explaining to ourselves what we think is.
That's something we have known all along. It does not conform with reality. For us, it is not a reason to give up. We do not give up. We try to get as close to reality as possible.
Moshe, I didn't say that, Moshe. I didn't say to give up. But what I'm saying is, confusing.
So don't tell us ever again that what we have does not conform to reality.
Okay,
do not need to be
I understand.
Philosophy and mathematics are human constructs.
Moshe, you are the final authority, Moshe. I understand. We can't debate because you're the final authority.
Oh, well, that's a little bit unfair. I mean, I think it's,
Yeah.
look,
Good debate. Yeah, it's good.
reality is a tough
assuming-
concept,
We
right?
are assuming that our feeble attempt describes reality.
You
But-
repeat yourself again.
My issue in general is like,
I'm not saying to give
one
up.
has to have intellectual humility, but one also has
Yes,
to have a degree of
yes.
optimism in order to do science, I think. And to me, like even this idea, like this meme, right? That's like humans are so feeble-minded and we're so egocentric and we are always thinking that we're so great and able to understand everything, but the universe,
Right,
like, care about us, blah, blah.
exactly.
Like that's just
It's all
like,
about egocentrism.
right. It's just, to me, that's just like a meme, right? Like when we say something like the universe doesn't care about us, I think we have to take that in like a really radical sense that like the universe could also care about us. Like in other words, the universe is beyond
Ah.
caring about us and also not caring about us. Like in other words, the
Caring
universe
is a human
transcends-
emotion.
No, I mean, like,
Caring,
the universe transcends like the concept of caring about us itself, right? Because like we're part of the universe, like we care about us. You know what I mean? Like we're here, like we're part of reality. Like this idea that we're constantly separating out, like, well, there's reality and then there's humans and their egos seems to me like, premised on this like separation between us and the world that's like kind of impossible.
Mhm.
I mean, we're like the universe trying to understand itself. I mean, we get to be as part of it as anything else, right?
Ah.
But yeah, I'll send a link to a cool essay by Heisenberg and some nice essays by Bohr, who I like for this sort of way that he uses language and his concern with like trying to make quantum mechanics concrete through the emphasis on like how you build like these apparatuses that measure things. And Schrodinger's interesting because he's sort of a mix of like he's sort of in the middle. Like sometimes there's some surprisingly radical metaphysical statements you'll find in Schrodinger, but
caring is a human. Schrodinger hit a roadblock when he tried to solve his equation. He found out that his wave equation did not give him an answer in real space. That's why Born was called on to pull the Born rule out of his ass. There's no logic to the Born rule. I'd like for somebody to give a lecture on the Born rule. What's the logical basis for it? There is none.
I mean, it's
Except
like
that it matches.
Let me make one comment here. Maybe you are right, Michael. Maybe there is no logical base whatsoever for the Born rule. In this case, I would say this is the most amazing rule ever conceived by mankind, because this rule is so true, it is so valid, it has been substantiated and proven to be correct so many times. It is amazing that someone conceived this rule without any reason whatsoever.
You know what's more amazing, Moshe? The concept of God is more amazing. It explains everything, if that's what you want to believe.
God. And God's cool, Yeah, well, I mean, more recently, like thinking about this cubism stuff has made me think. I definitely sort of think about the Born rule in a different way, because they're, the same thing is formulated like not in terms of the complex numbers and everything, but you in this completely different sort of more sort of normal probability looking like formalism. So I feel like there's like a lot to be said about it still. You know what I mean?
I think important viewpoints mean that there's no kind of easy way, but it's fact that Born rule works. We have variations around it, but you can justify it simply saying, well, if I consider a set of possible mutually exclusive outcomes, and if I allow linear combination of whatever kind of functions would be representing them, some kind of linear space, because if you have complex numbers, naturally the question is what is happening when I take the magnitude of a vector when in this space, and then kind of the Bohm rule justifies it, and it can also justify the renormalization, because if you're working with kind of incomplete set of numbers, frequency measurements, I mean, the more you improve it, the more you can keep actually normalizing your wave function to 1. But once you reach to complete set of possible outcomes, basically that's it. I mean, then you have to see how things are changing only between them.
Yeah, it's like I often think about it like geometrically, like you think about it like, well, there's lots of different representations of like the rotation group, but only when you're considering these complex representations, like we use in a qubit, can you use a 2-dimensional vector space. And 2 dimensions is exactly the number of possible outcomes to these experiments of the spin. So by like using the complex representations, you're actually like able to have the dimensionality correspond to the number of outcomes to your experiment, which is nice. And then, as I say, these cubists have a whole other take on it, I suppose, where you're sort of looking at the, basically the inverse of the Gram matrix of the inner products between the Pavum element as essentially giving you the Born rule. And so something having to do with the coherence between those different measurements. And so in a way you can look at that. So, and that introduces like negative numbers. So either you're sort of working with a quasi-probability distribution, if you transform the probability vectors, or you end up working with like a quasi-stochastic matrix, if you imagine it being in part of the time evolution. And so, then you sort of like, it gets into the interpretation of like, of negative probabilities and stuff like that, which often have to do with a situation where, your intervention in a system changes the underlying thing. Like there was a really great, very like intuitive example of like where like negative probabilities come from that I found the other day. Oh yeah, I sent it to my friend. Wait, I'll show it to you guys. You might appreciate it. Because I keep trying to think of like concrete models of like that sort of thing. Jeremy. Oh yeah, here. Peponi's thought experiment. A machine produces boxes with pairs LR of bits. So if there's a left bit, a right bit, they can be 0 or 1. In any run of the experiment, exactly one of the following 3 tests can be done. Look through the left window and observe L, look through the right window, observe R, or, right, like you can test whether L equals R without like actually looking at them. And then you do some experiments and you always find these results. In the left window, you always see 1. In the right window, you always see 1. But when you test whether the left and the right are the same without looking at them, the 2 bits are always different. So, but then if you like try to work out like probabilities for like the 4 possible outcomes of 2 bits, you're like, well, if in the left window you always see 1, that means that, probability of 1, 0 and 1, 1 has to be 1. And if, you always see 1 in the right window, then the probability of 0, 1 and 1, 1 has to be 1. But then if they're always different, the probability of 0, 1 plus 1, 0 has to be 1. And so then you solve that and you're like, you get these quasi probabilities. So P0, 1, P1, 0, and P1, 1 all have probability 1/2, but P0, 0 has negative 1/2. And so it's like clearly like the failure of like the normal concept of probability comes from the fact that like, in a sense, you could imagine these bits, being generated like on the fly based on what you decide to measure. And so like the error was in thinking that like there were some bits there before you looked, so to speak. And this, and obviously like you could have a computer do this. It's not quantum mechanical in any way. It just like is a situation where the result you get depends on how you go to elicit the result. And so that gives rise to negative probabilities. With the Pavim formulation, you can sort of excise all the complex numbers. And this is also true for all the quasi-probability formulations, like the Wigner formulations of quantum mechanics. And so instead, the difference is that you're working with, potentially negative probabilities or negative conditional probabilities. And then you can sort of view that as arising from the fact that, you're measuring stuff messes with what you're measuring. I mean, that's kind of like that's another way in my head recently I've been thinking about how to justify the Born rule, where it comes from.
And Wigner really was living in fantasy land for most of his life. Wigner's friend, are you kidding me?
Why is it always only got to cast aspersions on some of our
Because the thing is, I'm not criticizing their intellectuality. What I criticize is the fact that we accept things without proof just to make them match the measurements. End of story. And then when there is an alternative theory, like Bohm's theory, they don't even put it in college textbooks. That's crazy.
I completely agree that they should absolutely 100% have a chapter on Bohmian mechanics in all quantum mechanics textbooks. I completely agree with you. But as I think there are reasons when you do look at the theory to,
The reasons are political. He was an outcast.
Again, I like Bohm,
if they could,
and I know about his theory. And for me, it's like I am more willing to give up realism and than I am locality, and I have no problem with indeterministic theories, and so that's just like not an issue for me.
Wait a minute. Wait. Do you believe in entanglement? Entanglement is non-local. That's been proven experimentally.
I think we have made a full loop. We have gone back to the beginning. And I think that means maybe time to call it a night. It's been really
look, Matt, I want to apologize. I want to apologize for all of my colleagues for their terrible behavior.
Oh.
I wish they could all be like me. I'm sorry, but I want to apologize to my colleagues' behavior.
Okay.
This is unacceptable.
Well, no, I love you, Michael. Thank you always for coming.
No, that's true.
I love everybody. I love the world. I especially love the universe.
Yeah,
by
we're
the way.
all one. That's the Bohmian spirit.
Guys, I just Googled Bohn's rule, and there is an article in Quantum Magazine that explains to you where the Born rule comes from. It justifies the Born rule. And in the article in Wikipedia, they give you several pointers for justifications of the Born rule. I haven't read any of those articles, so I cannot comment about them. But obviously, there is quite a bit of discussion available out there about the foundation, the justification for the Born rule.
Yeah, actually.
And it's backwards. It's backwards reasoning.
Okay, that's unfair because I mean it's like especially like you can't hold these ideas like the people in the ferment of discovery in the 1920s like accountable for all this stuff. I mean, there's been 100 years of like meditations about this. Like, of course, at the beginning, like they were working blind, like in the dark.
No, but de Broglie pointed out their mistake at the 1927 Solvay conference, and he was shot down. He was shot down by Wolfgang Pauli with the approval of Niels Bohr.
I mean,
and de Broglie, who was shy, never brought up the subject again until Bohm did.
False. I mean, they recently like published like the transcripts from that conference, and you can see that they spend like a long time talking about the pilot wave theory, but multiple days, but whatever.
Well, Roy did not do a good job of explaining it then, but I know Pauli shot him down. Pauli was famous for this. Pauli shot down C.N. Yang when he came up with Yang-Mills theory. Pauli didn't like it and shot him down at Princeton University. But guess what? C.N. Yang has the last laugh. He's 98 years old and he's still living. He's still alive. He lives in Long Island.
Well, that's cool. I appreciate that. Recently, I can't necessarily say that this paper is 100% on point, but I saw it the other day and it has the benefit of being like 3 pages long. So you can, decide if you like Sabin Hassenfelder's sort of derivation of the Born rule from almost nothing. There are many such attempts. One should you should definitely look at like, Gleason's theorem.
But it's ass backwards reasoning, Matt.
Okay.
It's
Let
really...
me quote to you what Born said about how he derived his rule. Born said the following: the square of the optical wave amplitude, it was derived basically from Einstein's photoelectric effect where he was talking about particles of light, which Einstein proposed in 1905. The square of the optical wave amplitudes as probabilities density for the occurrence of photons. This concept could at once be carried over the psi function. So basically he got it from what Einstein said about the probability of finding a photon where you have a wave of light.
Hi, Moshe. If you read my emails, I explained where he got it. The energy, no, it's simple. The energy of a physical wave is proportional to the square of its amplitude. That's probably where he got the idea.
Yeah, exactly.
Right. That's not even Einstein. That's Maxwell. It's a mechanical wave. The square of the amplitude of a mechanical wave or an electrical wave is proportional to the square is proportional to the energy, not the amplitude itself. That's where he got it.
Yeah, when we did our structured Gaussian beam stuff.
But it's backwards reasoning. He pulled it out of thin air so it would match the measured results, and he was lucky. Got it right.
Yeah,
but Bohm has
Bohr.
Has the actual
imagine coming up with Bohr's model of the hydrogen atom. I mean, an insane, stroke of genius. He's sitting there, everyone's they got the plum pudding model. They got all these like ridiculous sort of
Bohr
models of the atom. And
Bohr's model was wrong.
Bohr's sitting around. Yeah, I know, but it was like 1912 or something. And like, it kind of works for like a lot of stuff. It's amazing, right? It's just like, this sort of insight that like, well, the electron would, if it really was just orbiting, it would, circle closer and closer to the nucleus. But, what if it formed a standing wave? And then you just, they didn't even have a concept of superposition or anything. They're just like, the phase space has been discretized. And so you just get one of these separate energy levels. And like that, yeah, you're right. Like that rule doesn't always work basically, but like the cases where it works, like it does work. Like you can kind of get the harmonic oscillator from that. You can kind of use this like quantization rule, like in a surprisingly large number of cases.
Look, I am not
all of early quantum mechanics, all of quantum mechanics for the first basically 3 decades of the 20th century is like, it's all fucking insane. It's like all people taking stabs in the dark. So it's just not fair to be like.
But it's got to be updated. Look, Newton was one of the greatest geniuses in history, but he wasn't right about everything. I'm not questioning the intellectual.
Right, like none of us are.
I'm not questioning the intellectual capacity or the great accomplishments of these early quantum physicists. What I'm objecting to is that it hasn't been updated because they suppress knowledge. for political reasons.
I just don't think it's true. I mean, I'm saying like.
So why don't I read about
Bohm?
Bohm's theory or even the pilot wave theory in a quantum physics textbook? But I read about nonsense like many worlds? Give me a break.
Well, you know, I would say it's because many worlds is like.
It's because Bohm was a communist and he was an outcast and he renounced his American citizenship.
I've
been afraid to
completely
touch him
agree
since.
that the consequences of that continue to echo to this day. Like,
Yes.
no doubt, like absolutely, for sure. But like at the same time, I mean, it's like, you know, people interested in many worlds, like it's sort of clearly applicable like to like any version of quantum mechanics, not just like non-relativistic.
Matt, it's applicable to nothing. It is fantasy. It is not physics because it cannot be verified. So it's not.
Like, I'm just saying why people like it.
It's not physics.
People work on Bohm. I mean, heck, someone posted that thing to Twitter.
Bohm is physics. Bohm is verified.
Literally, someone on Twitter was like, hey guys, look at my Python GitHub repository. I can calculate Bohmian trajectories.
Yes.
That suggests it's not like some dusty old theory that no one cares about because David Bohm was communist. It suggests that people do care.
It's only in recent years that his theory has been revived.
Comes up.
It's only in recent years because now we realize that the McCarthy era was a black mark on American history. But for the longest time, he was an outcast, and he died an outcast in a foreign country. But the thing is,
it really does. No, it really does kill me. It is a tragedy. I mean,
why haven't the textbooks been updated? Why isn't the textbooks talk about fantasy and they don't talk about physics? Everything Bohm said is verified. And by the way, John Bell said that Bohm's theory was the closest to reality. So why is it we read about fantasy like many worlds when we don't even read about a deterministic verified theory like Bohm?
I love
politics.
I love the way that you just define what fantasy.
Michael,
because
the question.
Whatever.
The question. The reason is that Bohm was accused of being a communist. That's the answer to your question. Now
that is the answer.
Okay.
What's your explanation?
I mean, I think every textbook should have, you know, like all 7,832 theories of quantum mechanics. Like there really should be a huge, you know, go into, because there's a lot of them and they're all interesting in their own way.
Yeah, but Matt, you know what the problem with 21st century physics is? That unproven or even unprovable theories like string theory, I may as well say it, they take all the oxygen out of the room. String theory gets funding and actual physics research, the funding is taken away from actual physics research. And this is a problem. This is a very big problem.
I'm not sure.
They canceled the super collider in Texas for political reasons. So now if you're a particle physicist, you got to go to CERN or
That's a different thing.
But Susskind gets funding and Brian Greene gets funding for nonsense? Come on.
Okay.
And I do not get funded.
How much do you need, Moshe? I charge a very high rate of interest. I charge a very high rate of interest and I have a lot of Italian friends. So be careful.
Like you guys, you know, like Michael, you're so interested in characterizing like physics or like whatever. You know, every other day, I go on the archive and I go down here and I look at quantum physics new, you know, all these things. Yeah. And I like, look, I just go through these and I like see what people are talking about. Like, do you do that? Because I would say if you don't, you have no fucking clue what's going on.
Actually, I do. But you know something? And I got to say, one of the members of the other group, who's a mathematician, is only interested in these, you know, hypothetical math theories regarding physics. And if you question any of his beliefs, his head explodes. So all these papers, you know, they're fine. And, you know, but they're not physics until there's empirical evidence for them. That's the bottom line. Let's call it what it is. It's math. It's not physics.
Yeah.
Until there's empirical evidence.
Yeah, for sure.
End of speech. I want to apologize again for my colleagues.
I have to say, maybe it is my background in the arts or whatever. Like, I just, always think about this novel, Against the Grain, by this sort of like late 19th century writer, Huysmans. I just always like found this funny, this sort of, he was basically like a late 19th century hipster. Like he was this sort of rich guy who he's just so bored and he's just constantly looking for like new sensations. He's like so bored, he like builds a smell piano where you press the keys. And
Did his daddy tell him about sex?
Who's he?
Unclear. Huysmans, yeah. He'll like be like, I have to go to Britain, but then he'll get distracted on the way there because really he just was hungry and it's like ends up at a cafe, like eating some like, British food or whatever. And, in the late 19th century, there were like a lot of people who, Oscar Wilde, art for art's sake, right? There's a big movement, art for art's sake, fuck practicality, right? Because this is like a lot of artists, reacting against 19th century capitalism. And, they're like, I love useless things. Like if something's useless and completely disconnected from reality, like that, like really turns me on, And you see that also in mathematics, like with that statement by Hardy in like A Mathematician's Apology, where he's like, what I love about math is that it's completely divorced from the practical world, right? It's not about money or reputation or anything. No one can use it for anything. And that's why I like it. And I have to say, I love quantum computers. I love being able to prove things with experiments. Like I love like actually making progress and like et cetera, et cetera, et cetera. But like a little part of me just loves useless shit. I think in some ways the useless is more beautiful. It's like, it's like, wait, it's like, what is it? You know what I mean?
But Matt, that's art. That's not science. And you have to make the clear distinction.
That's what I'm saying. So I agree with you. But you say it like it's a bad thing. But there's like a little place in my heart where I'm like, I like it when it's useless. I'm
not saying it's a bad thing, but we have to make the distinction. We can't allow people like Leonard Susskind to go on YouTube and profess that his mathematical theories are science when he knows it's not, and when he knows that it can't be proven in his lifetime or maybe ever.
But that's like not really quite fair, because
why not? It's math. I'm not criticizing it. I'm just saying I'm calling it what it is.
Provable. You know what I mean? Like, at least a mathematician in the old Platonist school would just tell you, I don't care if it's true, right? Like, they would say that to you. Like, like, that's part of my identity.
That's fine.
That's how I think of myself.
Science.
But
that's fine. Perfectly fine.
But Leonard Susskind wouldn't say that. Like, he genuinely thinks it's testable. In which case,
who's Susskind?
It's just
why isn't he in the lab testing it?
Testable. Like, you know what I mean?
Look, you know who Peter Woit is? You know who Peter Woit is at Columbia University? He's the anti-string theory guy. I'm surprised they let him work there, because Brian Greene runs the place.
But okay, I get it.
Peter Woit
I'm so tired of hearing about. I'm so tired of hearing about like whether string theory is true or not. Like, I really don't care.
Fine, that's your philosophy.
What do you mean,
it's
like
not science?
Like, it's not. No, I just mean like, I just don't think it's a big deal, or like even like anymore. Like, you know what I mean?
Big deal when it takes funding away from real science. That's a big deal.
I don't know if it's really that big of a deal though.
When they cancel the super collider because it's too expensive, but they're going to send idiots to the moon.
Sure that was like
Donald Trump to Mars.
Am I wrong in suspecting that was a bunch of Republicans? Like, I'm not sure. Like, I don't know.
Oh no!
Like, I'm just gonna go out on a limb.
It was actually President Clinton. It was actually President Clinton who called Ann Richards, who was the Democratic governor of Texas at that time. She predated George Bush, and Clinton said, You know, we're in an age of budget cuts, and you've got 2 big federal programs in Texas. You've got
Okay.
NASA, the
Was
space.
that before or after 94 or whatever, or 90, whenever the midterms were?
Well,
Like,
it was the 90s. No, but it was during the Gingrich revolution.
yeah,
But even
exactly.
Clinton
Yeah,
said,
that's my point. Yeah, totally.
Clinton said, but Clinton agreed. Clinton said the era of big government is
Oh,
over.
yeah, well, fuck Bill Clinton.
Yeah,
But he
right.
canceled the super collider.
Yeah, but so what's the point though? I mean,
The point
Americans
is
are
it makes us
insane.
a third-rate. It makes us a third-rate scientific power, and Europe and China will now be in the forefront of science, not the United States anymore.
I mean,
That is the
I
point.
hate to pose things in terms of national rivalry, but
Well, if you
yeah,
want to
I mean,
live in a
Americans
third world
have like
country,
a
you're
really
welcome to it.
Americans have a really weird relationship to science. I think that's what's going on here. Like, not like string theory sucking up all the funding. Like, that may have been true for a second, but like, I think there's like a deeper, more profound issue about
It's fantasy,
Americans'
it's
relationship to science.
anti-intellectuality. This country has always been anti-intellectual. It's a cultural thing.
Well, but
We
now-
celebrate the guy who dropped out of 3rd grade and became a billionaire. That's who we celebrate. Or
But-
sports figures who got into
Oh, yeah.
college
Now
because
it's
their high school
like
teacher
even more
lied.
The United
interesting.
States has more Nobel Prizes than any other country. More Nobel Prizes per person than any
So how
other.
come we don't have a super collider, but
We
Europe,
get more
which is
Nobel
in the
Prizes
poorhouse,
every
does?
year, more than any other country. I think this counts for something. Now, as far as string theory, I don't know of any other attempt to get to quantum gravity any closer than string theory.
Well, you're making an
Well,
assumption.
quantum
You're making an
gravity.
assumption that
Quantum
gravity is a
gravity.
quantum theory. There's no evidence that gravity is a quantum theory.
Shut up, let me finish. String theory is a quantum theory and it includes gravity. It's the closest we've come so far to quantum gravity. It's not the answer yet, but it's the closest we've come to it. If you know of anything that's closer than string theory, if you know of any theory that is a quantum theory and includes gravity, speak up. Otherwise, don't mention strings anymore.
Moshe, you didn't hear a word. You didn't hear a word of what I said. There is no physical evidence, no empirical evidence that gravity is even a quantum theory. We talk about gravitons like somebody actually discovered them. Show me a graviton anywhere. We don't know if gravity is a quantum theory, so they're all spinning their wheels.
I just want to go back to Moshe's comment before, which was something like it's one thing if we're being like, hey, random person who only reads pop sci articles and just like believes like, oh yeah, the physicists and their graviton.
That's the
their
average
universe
American.
is. Like, I get that like you're kind of on a crusade against like the bullshit that is promulgated in the media and like people lap it up or like whatever. But I think for these meetings, I think we should all just like be on the same page that like we're well aware like what the space of the theories is like, what they say, what they don't say, what's kind of tendential, what's been proven, what hasn't. The gravitons are like this, but we haven't seen them, etc. Like, I think we all know this.
No, and I agree with you. We should stick to the subject. But I thought we had reached happy hour, and I'm just trying to make everybody happy.
Please, don't let me stop you.
And apparently Marty is the only one who
I mean,
appreciates
no,
my.
I read about the pilot wave in a book by Green.
The irony. Oh my God.
Yeah, but he doesn't really believe it, does he?
Okay.
Well, he listed about a dozen different theories.
Yeah, right.
One
Yeah,
of them.
exactly. Look, Brian Greene is a showman. You know, his wife is a so-called movie producer. He's got all the contacts in media. He's a popularist. He's not a serious scientist.
If you told us this.
I know, but maybe you don't remember.
You told us so many times, there's no way we'll never forget it.
I thought you weren't there when I said it last time. I wasn't sure.
I don't know if it was last time, but I heard it from you many, many times.
Well, see, Michael lives his beliefs. He's completely deterministic.
No, I believe in science. I don't believe in fantasy. The average American would like to believe in fantasy. That's where they live. That's why they watch bullshit on television. They go to the movies when there isn't a pandemic and watch bullshit, and they think it's science. What was that? Interstellar, which they claimed, matches real science. Give me a break.
Well, at least, I mean, that was a clever way of getting funding, I suppose, for doing the simulation.
Yeah, but it's not science. It's fantasy. And people want to believe in fantasy. Human beings have a tendency to want to believe in escapism because life is tough for a lot of people.
Yeah.
So escapism during the Depression, movies made a big hit during the Depression because it portrayed normal life when everybody was living in poverty. People love escapism.
It's a good
But
point.
that isn't science. Fantasy is not science.
Michael,
Never confuse the two.
all of us are participating in this session right now. This session is escapism. All of us are busy escaping right now. You're also escaping right now.
I'm escaping too, and I apologize for Moshe, for Marty, I apologize for everybody. I wish everybody could be as polite as I am. I apologize for the rest of you, but you're excused.
On that note, I have to go eat dinner, but it's been lovely as always. Talk to you guys.
Thank you, Matthew. I really appreciate. Thank you very much. And
Oh, yeah.
your discussion of the quantum reference frames. This was very, very nice.
Awesome. Yeah, I'm glad that came through. I wasn't sure, I sort of saved it towards the end. I wasn't sure if I was.
And by the way, I also appreciate the participation of all the participants, even Michael.
Well, especially Michael. Especially Michael.
I get a
Thank
lot
you.
out of Michael's statement.
Michael who?
And I also
statement.
appreciate the inputs from Georgiev.
Yeah, definitely.
I'm definitely a
Oh,
determinist.
you're welcome. Glad to have been of help.
Some good insights, very good insights.
And he's very patient too. I want to compliment him.
That's
He's very
right.
patient.
Yeah.
We all appreciate
Yeah.
the patience, Georgiev.
Thanks a
You're
lot,
welcome.
Matt.
Yeah.
See you next time.
Bye.
Thank you.
Thank you again.
Bye.
Bye-bye. Stay safe.
Yeah, you too.
Thanks.